Welcome back to the Snoozy Scientist, your quiet place to drift into rest while still letting curiosity roam. Tonight, we're traveling far deep into Earth's past. You see, Earth is not the steady, predictable home we imagine it to be. Across its long history, a strange pattern has emerged. The planet has transformed again and again into a frozen giant. Ice sheets kilometers thick have pushed across continents, sea levels have fallen by hundreds of feet, forests have vanished beneath endless white, and countless species have been forced to move, adapt, or disappear altogether. And over the last million years, something unusual becomes clear. This frozen world does not return at random. It follows a rhythm, a repeating chill that comes back roughly every 100,000 years. Scientists can see it everywhere they look, in deep sea sediments layered like pages in an ancient diary, in tiny air bubbles trapped inside Antarctic ice, and in the rocky grooves carved by long vanished glaciers. Together, they reveal a pattern as steady and powerful as a slow planetary heartbeat. And this rhythm raises questions that linger like a whisper at the edge of understanding. What force could reshape an entire planet so dramatically and so predictably? Why does the freeze return with such remarkable consistency, as if Earth is answering to a clock no one can see? Why 100,000 years and not 10,000, or 50, or a million? What tells the planet when it is time to begin its next long descent into ice? And perhaps most quietly unsettling of all, is the next great winter already beginning its distant approach? Tonight, we'll drift through the clues hidden in ice, rock, oceans, and sky, following the trail of this vast planetary heartbeat and gently exploring where we might stand within its long repeating cycle. But before we begin, I'd love to know, where in the world are you listening from tonight, and what time is it there? Your comments are one of my favorite parts of this sleepy little community. If you're enjoying these late night explorations, a like and a subscribe would mean a lot. And for those already subscribed, thank you for being part of this calm little corner of science. Now take a slow, deep breath. Let your shoulders relax. Close your eyes if you'd like. And together, let's drift quietly into the long rhythm of ice that has shaped our world again and again. To understand the long rhythm of cold that shaped our world, scientists first had to find places where time moves slowly, not the quick ticking of days or years, but the patient settling of stories that drift quietly downward, one grain at a time. These stories hide in the deepest corners of the ocean, in frozen air sealed beneath ancient snow, and in the scars left across the land by ice that has long since melted away. Each record holds a different voice from Earth's past, and when listened to together, they reveal a pattern that feels almost unreal in its scale. Far beneath the waves, the ocean floor grows in thin layers that take shape so gradually that an entire human lifetime is no more than a whisper across their surface. When research ships lower hollow tubes into the seafloor and lift them back to the light, what emerges looks simple at first, just a column of packed mud, fine as sifted flour. But inside those layers are tiny shells made by plankton that once floated in the sunlit surface, far above. These small organisms built their delicate homes with minerals drawn from the surrounding water. The chemistry of those minerals changes slightly as the ocean warms or cools, so each shell carries the faint signature of the water in which it lived. When scientists examine these shells, they read temperature the way one might read tree rings. Warm periods leave a different pattern from cold ones. Over time, the layers reveal a gentle rise and fall that stretches across hundreds of thousands of years. The cool periods deepen, then soften, then deepen again, a slow pulse recorded in the quiet dark of the sea. This ocean memory is one of the clearest witnesses to the ice ages, and it shows that the cold did not arrive suddenly. Instead, it grew step by step, year after year, until ice sheets reached far beyond their polar homes. But the deepest memory of all lies in the frozen heart of Antarctica and Greenland. Here, snow falls lightly each year, then settles beneath the next snowfall, and the next after that. Over countless millennia, these layers compress into clear blue ice. What makes this ice extraordinary are the tiny bubbles of ancient air that become trapped inside. These bubbles are small enough to hide unnoticed, yet they carry the atmosphere of long vanished worlds. When researchers drill deep into the ice and pull up the long white cylinders known as ice cores, they bring with them a frozen library of Earth's breath. Inside these cores, every layer is a page. Dust swept across the continents during colder, drier times settles in pale bands. The levels of carbon dioxide rise and fall in rhythm with the planet's shifting warmth. Even subtle traces of temperature can be read in the chemistry of the ice itself. These frozen records stretch back far beyond the limits of human memory, providing a glimpse into climates that shaped the migration of early life and the landscapes beneath their feet. As the cores descend deeper into the ice sheet, the years roll backward. Warm periods glow as thin, clear layers. Colder ages appear as thicker, clouded bands filled with dust from a parched world. In some sections, the ice is older than human language, older than the first sparks of art or story. It holds the marks of many cycles, each one a reminder that Earth has long followed a repeating path from warmth to cold and back again. Yet the signs of these ancient freezes are not found only in the sea and ice. Across the continents, the land carries its own quiet testimony. When glaciers move, they do not glide smoothly. They press against the ground with a weight so immense that stone itself bends and breaks. As the ice grinds forward, it leaves behind long parallel scratches on exposed bedrock. These scratches, called striations, point like arrows in the direction the ice once traveled. They can be seen on mountainsides, river valleys, and high plateaus, each one marking a journey that ended thousands of years before the first cities rose. Along the edges of those ancient ice sheets, the land is shaped into low, curved ridges known as moraines. These ridges form as glaciers push soil, boulders, and fragments of stone into great arcs that trace the outline of the ice's farthest reach. When the ice finally melts, the moraines remain as reminders of the moment when the cold stopped its advance. Sometimes the glaciers lifted giant stones from their native homes and carried them for great distances. When the ice melted, these stones, called erratics, were left resting on open plains or forest floors with no explanation except the long vanished force that once delivered them. Their presence reveals the true scale of the ice sheets. They show that the glaciers once stretched far beyond their modern limits, crossing landscapes that today feel temperate and peaceful. By bringing these clues together, scientists reconstruct the timeline of past freezes with remarkable clarity. The layers of ocean mud reveal the slow sway of temperature through the ages. The ice cores provide a detailed record of atmosphere and climate. The landforms show how far the ice reached and how it changed the world as it moved. When these records are aligned, they match with surprising precision. A cooling in the ocean corresponds with a thickening of dust in the ice. A shift in carbon dioxide aligns with the advance of glaciers across the continents. Piece by piece, the planet's story takes shape. This is how we know the ice ages happened and how we trace their rhythm across time. The evidence lies in quiet places, waiting patiently for someone to listen. There comes a moment in Earth's long rhythm when the cold reaches its deepest breath. It is a point where the slow steps of cooling that began ages earlier finally settle into their fullest shape. Scientists call this moment the last glacial maximum, a time roughly 20,000 years ago when ice held more of the world than at any point in recent memory. It was the height of the most recent great winter, and the planet looked very different from the warm and familiar one we know today. Much of the northern hemisphere lay beneath vast sheets of ice that rose in silent walls of white. These sheets were not thin blankets, but towering expanses that stretched across the horizon. They covered what is now Canada, the northern plains of the United States, the valleys of northern Europe, and wide regions of Siberia. In some places, the ice stood taller than mountains, its weight carving deep basins into the land. The world here felt locked in a quiet stillness, as if time itself moved more slowly beneath so much cold. Even far from the poles, winter lingered in a way that shaped every detail of the landscape. Forests withdrew into narrower bands, grasslands became colder and more windswept. Rivers ran along different paths, pressed aside by the presence of so much frozen mass. The air carried a sharper bite, and the sunlight lingered in softer hues. Beneath this pale sky, the planet reached the fullest extent of its icy reach. With so much water held in frozen form, the oceans fell to lower levels. The sea pulled back from the continents, revealing stretches of land that lie hidden today. The shoreline extended outward by distances almost impossible to imagine. If one could walk along those ancient coasts now, the world would feel larger, the horizon more distant. Scientists estimate that the sea level dropped by more than 400 feet during this time, enough to expose entire regions that later vanished beneath rising waves. These newly revealed lands formed natural bridges between continents, where today water separates Siberia from Alaska, a broad expanse of grasslands once stretched from one side to the other. This region, called Beringia, became a wide passage shaped by cold winds and low seas. Fintum, it was neither forest nor frozen desert, but a mix of tundra and dry steppe that supported an entire community of life. For early humans, these shifting landscapes opened paths that had never existed before. The people of that time lived in small, resilient groups. They followed herds, tracked the changing seasons, and carried with them stories shaped by the world they walked across. During the last glacial maximum, these groups moved slowly across the exposed land bridge from Asia into the Americas, following animals and seeking safer grounds. Their migrations were not fast journeys, but gradual steps influenced by weather, food, and the quiet pull of curiosity. Other regions of the world saw their own movements shaped by ice and low seas. In Southeast Asia, large islands were connected to one another, forming a single continuous landmass. Humans living there traveled across plains that are now submerged beneath deep ocean water. In Europe, valleys blocked by glaciers offered narrow passages between cold barriers. People gathered in sheltered regions where food remained stable and winters less severe. The world was not empty during this time. It was home to extraordinary creatures that had adapted to the cold. Mammoths roamed the grasslands with their thick coats catching the sunlight in muted gold. Woolly rhinoceroses grazed along frozen slopes. Huge bison herds crossed open fields, stirring clouds of frost as they moved. Cave lions, with limbs strong enough to survive long winters, hunted in the dim light of glacial days. These animals were shaped by the cold, built to endure and thrive on the edge of ice. Yet even for these giants, the world was narrowing. As the ice sheets grew, the spaces where life could flourish grew smaller. Grasslands retreated, forests thinned, food became harder to find. Some species survived by following the shifting borders between ice and warmth, always searching for a place where grasses still sprouted or prey still gathered. Others were pushed into isolated pockets where they endured as long as the land allowed. Across the continents, life settled into patterns shaped by the cold. Days were shorter, nights stretched long and deep, and the horizon often shimmered with drifting snow. But within this quiet world, there was still movement, still growth, still the subtle pulse of Earth's story. Hunters left footprints beside those of mammoths, fires glowed within small shelters built against the wind, herds found new paths across plains where the sea had once rested. The last glacial maximum marked a turning point in the planet's long rhythm. It was the moment when the cold reached its widest reach, touching nearly every corner of the northern hemisphere and reshaping the paths of humans and animals alike. The earth stood in the quiet grip of ice, and everything that lived moved carefully within the narrow boundaries that remained. As the great winter of the last glacial maximum settled across the world, the deep forces that shaped it were already at work far beyond the reach of wind and snow. These forces did not rise from the oceans or the shifting continents. They came from the sky, from the quiet and patient way Earth travels through space. To understand why the planet slips into great freezes again and again, we step gently away from ice sheets and cold plains and look upward, where Earth's long path around the sun writes a slow rhythm across time. Earth does not move through the cosmos in a fixed and perfect loop. Its orbit changes shape over long stretches of time, almost like a breath taken so slowly that no single generation notices. Scientists who study this movement speak of the Milankovitch cycles, a name given to the repeating patterns in Earth's orbit and tilt. These patterns do not act suddenly. They unfold across tens of thousands of years, nudging the planet in ways that seem small, yet hold enough power to reshape the surface of continents. The first of these patterns lies in the shape of Earth's journey around the sun. It is easy to picture this path as a neat circle, but it slowly becomes either more rounded or slightly stretched. When the orbit grows a little more oval, Earth spends part of the year slightly farther from the sun than usual. The change is gentle, far too subtle for any single lifetime to notice, yet its effect grows over millennia. When combined with other shifts, this small difference in distance can adjust how much sunlight certain regions receive, especially during the warm months that determine whether ice melts or survives. A second pattern comes from the way Earth leans as it spins. The planet does not stand upright. It tilts, and that tilt wavers with time. Sometimes it leans a little more, and sometimes it leans a little less. These tiny adjustments change how strongly sunlight strikes different latitudes. When the tilt is greater, seasons become more pronounced. Summers grow warmer, and winters grow colder. When the tilt softens, seasons become milder, with cooler summers and gentler winters. It is this quiet sway that helps decide whether snow lingers year after year in high northern regions or fades away in the warmth. Along with these two movements, Earth also shifts its orientation in space. The planet spins like a top that slowly traces a circle as it wobbles. This slow motion alters which hemisphere tilts toward the sun at different points in the orbit. Over many thousands of years, this wobble changes the strength of sunlight that reaches northern or southern lands during their summers. Together, these three patterns weave a slow dance between Earth and the sun. None of them alone is enough to summon an ice age or end one, yet when they align in certain ways, the balance of sunlight changes just enough to let ice grow or melt. The changes in sunlight are modest, yet they fall upon the places most sensitive to them. In lower latitudes, sunlight is steady and strong. Seasons shift, but the warmth of the tropics does not depend much on slight changes in Earth's orbit. The story is very different in the higher latitudes. These regions sit near the edge of the cold, where every degree of warmth carries weight. Here, summer must be warm enough to melt the snow left from the winter. If that melting weakens even slightly for many years in a row, snow accumulates. Once snow begins to persist, it reflects more of the sun's heat back into space. Over time, These small changes create space for ice to build, then spread, then become the great sheets that define a glacial age. The high northern latitudes are especially important because so much land lies beneath them. Land absorbs and releases heat differently from oceans. Because of this, the northern hemisphere carries more influence on the growth of ice. When summers here become cool enough for snow to survive, glaciers can begin to reach outward. Even a small change in summer warmth, when repeated across centuries, can help tip the balance. It is in this way that Earth's slow orbital rhythms hold sway over the planet's long climate story. These changes do not roar with sudden force. They whisper across time, repeating the same patterns over and over. The frozen landscapes of the last glacial maximum, the low seas and wandering animals, the migrations of early humans, all unfolded under the quiet influence of these subtle shifts in the sky. By looking upward, we begin to see how the path of Earth through space becomes a guide for the planet's changing climates. The cycles continue today, steady and patient, shaping the long future, even as we live through a moment of temporary warmth. As we drift farther into the quiet machinery behind Earth's long cycles, we move from the gentle tilt of the planet to another motion that is even slower, almost too slow to imagine. This motion lies in the shape of Earth's path around the Sun, a path that changes so gradually that hundreds of generations may pass before it shifts enough to notice. Yet it is this slow reshaping that sets the rhythm of the 100,000-year beat we see written in ice and ocean. To understand it, we look at the subtle stretching of Earth's orbit, a change known as eccentricity. Most of the time, Earth's journey around the Sun is nearly circular. The distance between the planet and the glowing center of our solar system stays almost the same through the year. The sunlight we receive feels steady, softened only by familiar seasons, but over long spans of time, this nearly perfect circle begins to stretch. Very gradually, it becomes slightly more oval. The difference is gentle, like the soft curve of a fingerprint. It is not a sharp ellipse, only a slight lengthening that changes how far Earth travels from the Sun during part of its orbit. This stretching does not happen quickly. It unfolds across a cycle that lasts about 100,000 years. When seen over these vast periods, the orbit swells and relaxes like a long, slow breath. In one phase, Earth circles close to the Sun in a rounded path. In another, the planet traces a journey that takes it a little farther out at one point, then brings it closer again at another. The cycle repeats with patient regularity, rising and falling like the tides of deep time. Although the change in shape may seem small, its influence builds over thousands of years. When the orbit is more oval, the difference in distance between Earth's closest point to the Sun and its farthest point grows larger. Because sunlight weakens as distance increases, Earth receives slightly less energy when it is at the farthest part of its stretched path. When the orbit is more circular, that difference becomes much smaller, and sunlight arrives with more consistency throughout the year. This shift affects the seasons in ways that quietly shape the planet's climate. When Earth follows a more elongated orbit, the contrast between seasons can become sharper, especially in whichever hemisphere experiences winter at the farthest point of the orbital stretch. Winters there become cooler, summers become warmer, and this imbalance echoes through the atmosphere and oceans. When the orbit returns to a rounder shape, the extremes soften, the seasons grow closer in temperature, and the world settles into a gentler pattern. Yet the influence of eccentricity does not lie merely in warmer or colder seasons. It lies in how those changes interact with the tilt of the planet and the slow wobble of its axis. These three motions overlap like individual notes that blend into a single chord. When the orbit is more oval, the effects of tilt and wobble can become amplified, especially in the places most sensitive to small shifts in sunlight. High northern regions sit at the edge of this sensitivity, where even a slight cooling of summer can allow snow to linger, then stack, then form the first shadows of growing ice. In times when Earth's orbit is more circular, that sensitivity becomes softer. Summers in the high latitudes remain warm enough to melt snow that fell during long winters. Ice finds it harder to persist from one year to the next. The delicate balance between freezing and melting leans toward retreat rather than growth. This slow rhythm of orbital stretching has been one of the most influential patterns in Earth's climate history. It sets the overall tempo for the great cycles of cold and warmth that have shaped continents and guided the paths of early humans and animals. The 100,000-year timing seen in deep sea sediments and ancient ice aligns with this orbital pattern, offering a quiet reminder that Earth's climate has never been driven by a single force. Instead, it moves in response to a long conversation between sunlight, distance, tilt, and time itself. To picture this cycle, imagine Earth gliding along its path with small variations in its journey. When the orbit is stretched, Earth spends a longer period farther from the Sun, receiving sunlight that arrives with just a little less strength. This subtle reduction, repeated each year for countless generations, can tilt the balance toward the growth of ice. When the orbit returns to a rounded shape, the seasons regain their steadier rhythm. The world relaxes into warmth again, allowing glaciers to retreat and oceans to rise. The beauty of eccentricity lies in its quiet influence. It does not rush or force, it lingers, shaping climate through patience. Its cycle continues even now, repeating the same ancient pattern that has guided Earth for millions of years. As Earth glides along its long path around the Sun, another motion works quietly in the background, shaping the rhythm of warmth and cold that the planet experiences each year. This motion is not in Earth's orbit, but in the way the planet tilts. Earth does not stand upright as it spins. It leans gently, like a slow turning top, that never straightens fully, and over time, that lean changes. It grows a little stronger, then softens again, moving through a cycle that lasts tens of thousands of years. This slow shifting of Earth's tilt is known as obliquity. Although the word may sound technical, the idea behind it is simple. Imagine holding a globe and tipping it slightly forward. Now imagine tipping it just a little more, then a little less, over a long span of time. Earth behaves in this way, leaning first toward a stronger angle, then returning to a gentler one. The difference is small, but not insignificant. Earth's tilt swings between roughly 22.1 degrees and 24.5 degrees. Even this modest change has the power to reshape the seasons and influence the growth of ice across the planet. When Earth tilts more strongly, the contrast between seasons becomes sharper. Sunlight arrives more directly in whichever hemisphere is leaning toward the sun. Summers grow warmer, bringing longer days filled with more intense light. Winters grow colder, with shorter days and a deeper quiet. It is as if the tilt exaggerates the familiar rhythm of the seasons, pulling them toward greater extremes. When Earth tilts less strongly, the opposite happens. The seasons soften, summers lose some of their intensity, with sunlight arriving at a gentler angle. Winters become milder, with cold that does not press quite as firmly onto the land. The entire year feels more balanced, with a quieter flow between warmth and chill. These shifts in tilt may seem subtle on a human timescale, yet they play an important role in Earth's long climate story. The strength of summer, especially in the far north, determines whether snow survives or melts away. Snow that lingers through the warm months begins to build a foundation for ice. Over time, that stubborn layer can grow thicker, then wider, and eventually become part of a vast ice sheet. In high latitudes, where the sun sits low on the horizon and the seasons carry a delicate balance, even a small change in tilt has far reaching effects. When the angle is at the lower end of its cycle, summer loses some of its power. Snowfall from the previous winter melts more slowly, or in some places, not at all. Patches of white remain long after the solstice has passed. These patches reflect sunlight back into space. The land beneath them stays cooler, and the surrounding air follows the same path. From these small beginnings, ice can gain a foothold. In times when the tilt reaches the higher end of its cycle, the opposite occurs. Summers grow strong enough to erase most of the winter's snow. The sun climbs higher in the sky, sending warmth deep into the soil and across the open fields. Even regions close to the Arctic Circle feel this renewed strength. Ice that might otherwise survive fades away before the next winter arrives. Without persistent snow, ice sheets have little opportunity to grow. This gentle rocking of Earth's axis does not work alone. It joins with the slow stretching of Earth's orbit and the gradual wobble of the planet's rotation to shape the timing of the ice ages. When the tilt, wobble, and orbital shape align in certain ways, the conditions become just right for ice to grow. When they align differently, the world leans toward warmth. Each cycle contributes a note to the long, repeating pattern that scientists see in ocean sediments and frozen air. Obliquity is particularly important because it affects the places most sensitive to long-term climate change. High northern latitudes contain large expanses of land, and land responds more quickly to changes in sunlight than ocean water does. The tilt, therefore, has a strong influence on the balance between seasonal snow and enduring ice. A slightly cooler summer in these regions can allow snow to accumulate year after year. A slightly warmer summer can undo centuries of buildup. To picture the effect of obliquity, imagine standing near the Arctic Circle during different stages of the tilt cycle. In a time of greater tilt, the summer sun sits higher in the sky. It shines with fuller warmth, melting the snow that covered the ground all winter. The air feels open and bright, and the land breathes freely. In a time of lesser tilt, the sun hangs lower. Its rays stretch across the horizon instead of pouring straight downward. Summer still arrives, but it carries a quieter heat. Snow clings to shaded valleys and northern slopes, surviving just long enough to meet the next snowfall. This delicate balance, repeated across thousands of years, decides whether ice sheets grow or retreat. It shapes shorelines, guides migrations, and influences the long memory of the climate. Through all of this, the tilt continues its slow motion, shifting with the patience of deep time and adding its voice to the story of Earth's ever-changing seasons. As Earth continues its slow journey through space, another motion works quietly in the background, unfolding with a patience that belongs only to the cosmos. We have drifted through the stretching of Earth's orbit and the gentle shifts of its tilt. Now we step into a different kind of movement, one that feels more like a soft turning than a change in shape. It is the movement that gives Earth a subtle wobble, similar to the slow circling of a spinning top as it begins to lose speed. This long and graceful wobble is known as precession. If you have ever watched a child's toy top begin to lean as it spins, you may remember how the top's tip stays in place while the body traces a wide, gentle arc. Earth behaves in much the same way, although the motion is so slow that no person could ever witness it directly. One full sweep of this wobble takes nearly 26,000 years. During that time, the direction Earth's axis points shifts gradually, turning through the sky almost like the hand of a distant celestial clock. Although precession does not change the angle of Earth's tilt, it changes where that tilt aims. At one time in this long cycle, the northern hemisphere leans toward the sun when Earth is closest to it. Thousands of years later, the northern hemisphere leans toward the sun when Earth is farthest away. The reverse becomes true for the southern hemisphere. Over these long stretches, the strengths of the seasons drift from one hemisphere to the other, guided by the slow turning of the axis. This shifting orientation shapes the character of summers and winters across the planet. When a hemisphere tilts toward the sun during the part of Earth's orbit when it is closer, its summer becomes warmer and more intense. The sun shines more brightly, the days grow longer, and the warmth reaches deeper into the land. When that hemisphere leans toward the sun during the part of the orbit when Earth is farther away, its summer softens. The sunlight arrives with a slightly gentler strength, and the warmth that once filled those long days becomes calmer and more muted. This quiet exchange between strong summers and gentle summers travels slowly between the hemispheres. When the northern hemisphere receives stronger warmth, the southern hemisphere receives a cooler version of its own summer. Then, as the wobble continues, the roles change. Over thousands of years, the seasons drift like waves across the globe, rising in one half of the planet while softening in the other. Precession influences more than the simple balance of summer and winter. Its slow turning also affects the great systems of wind and rain that sweep across continents. In regions touched by powerful seasonal monsoons, the timing and intensity of rainfall can shift with the orientation of Earth's axis. When a hemisphere receives stronger summer sunlight, its land warms quickly. Warm land pulls moist air inland, and monsoon rains grow heavier. When the summer sunlight weakens in that hemisphere, the land warms more slowly, and monsoon rains become quieter. This slow pulse of humidity and dryness leaves traces in ancient lake beds and river sediments, marking the turning points of climates that shaped early civilizations. In the far north and far south, precession influences the survival of summer snow. At high latitudes where the sun already sits low on the horizon, a small change in summer strength carries great weight. When the northern hemisphere leans toward the sun during its closest approach, the increased warmth helps melt much of the winter snow that accumulated across the Arctic. When the same hemisphere enters its summer while Earth is farther from the sun, the warmth softens. Snow on distant slopes lingers well into the warm months. Some patches survive long enough to meet the next winter's snowfall. These lingering patches are the earliest shadows of ice, small beginnings that can expand across centuries if the pattern continues. In the southern hemisphere, the pattern mirrors this motion. When the southern lands tilt toward the sun at the closest point of the orbit, their summers deepen with stronger light. Glaciers in places like the Andes pull back, and meltwater feeds streams that run down into valleys. When the southern hemisphere's summer occurs at the farthest part of the orbit, the warmth eases. Snow and ice find time to accumulate, shaping the landscape in their quiet way. Precession does not act alone. Its influence blends with the variations in Earth's tilt and the slow stretching of its orbit. Together, these motions form a long, patient rhythm that determines whether ice grows or retreats. Precession guides the timing of sunlight. The tilt decides the power of the seasons. The orbit shapes the distance from the sun. Their combined effects become the heartbeat that leads Earth in and out of great freezes. To picture precession, imagine Earth standing in the stillness of space, leaning slightly and turning slowly, with its axis tracing a gentle circle across the sky. As that circle slowly shifts through time, the strength of the seasons drifts between hemispheres, shaping the breath of monsoons and the survival of snow. It is a motion that never stops, a quiet turning that has been steering Earth's climate for millions of years, unnoticed except for its imprint on the story of ice and warmth. As we drift deeper into Earth's long rhythm of cold and warmth, we arrive at a point where the great motions of the cosmos meet the delicate realities of the ground beneath our feet. The stretching of Earth's orbit, the slow rocking of its tilt, and the patient turning of its wobble all play their part. Yet the true turning point between an age of ice and an age of thaw lies in a place far more familiar. It lies in the summer sunlight of the northern lands, where the fate of vast ice sheets is decided by warmth that lasts only a few precious months each year. The northern hemisphere holds most of the planet's large continents. Where there is land, snow can build. Where snow lingers, ice can take root. Because of this, the summer season in the north carries an influence much greater than the warmth of the southern summer. Oceans dominate the southern hemisphere, and water absorbs heat, slowly buffering the seasons. But the north offers broad stretches of open terrain, high plateaus, and long mountain chains. These regions respond quickly to changes in temperature. When northern summers are strong enough to melt the winter snow completely, the land breathes freely and warmth holds its place. When the summers soften, even by the smallest amount, the balance begins to tilt. It takes only a narrow margin for ice to gain a foothold. The line between ice buildup and ice retreat is astonishingly thin. A slight decrease in summer sunlight, stretched across years, can allow snow to survive long after it would normally disappear. At first, it may be only a few patches of white remaining in shaded corners, tucked against rocky slopes, or hidden in the hollows of northern hills. These patches reflect sunlight more easily than bare ground. They stay cool, and the lands around them cool as well. In the following winter, snow settles upon a world that is already a little colder. Over many years, this small shift becomes something much larger. If summer warmth cannot overcome the snow from the previous season, the cycle begins to favor buildup rather than melting. Winter arrives earlier and leaves later. Snowfall increases in regions that once saw warmer summers. The land grows brighter under the long days of sunlight. But that brightness is not warmth. It is reflection, a way for the earth to send sunlight back into the sky instead of absorbing it. This is where the story deepens, because the growth of ice is not simply a matter of plentiful snow, it is a matter of snow surviving. A single unmelted layer from one summer can become the foundation for the next winter's snow. When the pattern repeats, layer after layer begins to accumulate. The weight of these layers eventually presses the snow into dense crystalline ice. That ice thickens, expands, and starts to flow outward like slow rivers of cold. The growing sheets reshape valleys, press against hills, and move cautiously across the land. It all begins with a single summer that is just a little too cool. Imagine standing in a northern valley during such a summer. The air is soft, and the light stretches long into the evening. Most of the winter snow has melted away, but in the shadow of a ridge, a thin blanket of white remains. It seems harmless, a quiet reminder of the cold months gone by. Yet this lonely patch holds the future of the climate in its delicate surface. If the next summer is equally cool, that patch will grow. If the summers become cooler still, the patch will never disappear again. It will become part of a new layer that glints under the sole, bouncing light upward, deepening the chill. Once this process begins, the landscape begins to change its own destiny. Ice is a powerful architect. It directs winds, alters storm paths, and lowers regional temperatures. Rivers shift to new courses as growing ice blocks their way. The land beneath the ice sinks under the weight, changing the shape of coastlines and the flow of groundwater. Each small patch of surviving snow is a seed from which a glacier can eventually rise. These early stages of ice growth matter more than the towering sheets that eventually follow. The beginnings are the most fragile part of the cycle. They can be undone by a return of strong summers or amplified by weaker ones. When northern summers lose just enough warmth to fail at melting all the snow, the world begins to drift toward a glacial age. This drift is slow, so slow that no generation would see its turning. Yet the evidence lies in the ancient records we explored before. in layers of ocean mud and frozen air that show the repeating pulse of cooling and thawing. The sensitivity of the North is the key that unlocks the planet's long climate memory. The high latitudes serve as the tipping point where small changes in sunlight become powerful forces. A slightly cooler summer in the tropics would pass with little lasting effect, but a slightly cooler summer in the north can change the balance for centuries. This quiet threshold, where ice either retreats or advances, has shaped the history of the Earth again and again. It is the delicate hinge on which entire ages turn, a reminder that the largest changes can begin from the smallest shadows of snow that refuse to melt. As the northern summer guides the fragile line between melting and survival, another force quietly waits to shape the direction of the planet's long journey. It is not a force of pressure or gravity. It is a force born from sunlight itself, a simple interaction between light and color that becomes powerful when repeated across centuries. This is the albedo effect, the gentle but persistent way bright surfaces reflect sunlight back into space, cooling the world in the process. The idea behind it is easy to see in daily life. Snow on a winter morning glows with a clean brightness that can almost hurt the eyes. Ice on a frozen lake gleams beneath the low sun, turning beams of light back into the sky like a mirror. Dark soil or open water, in contrast, absorbs the sun's warmth and grows warmer beneath its touch. In the high latitudes where the future of ice is decided, these differences in brightness carry enormous weight. When snow or ice covers the ground, much of the sunlight that reaches Earth is reflected upward. The land beneath remains cold, and the air that settles above it cools as well. In places where dark soil or stone is exposed, the sun's warmth sinks into the ground and makes the surface more welcoming to spring thaw. This simple contrast begins to guide the planet toward either warmth or deepening cold. At first, the effect is small, especially when only a few patches of snow remain from one summer to the next. The world can absorb those small variations without drifting too far in one direction. But snow that survives summer holds a quiet power. Each bright patch reflects more sunlight than the darker land around it. The surrounding air cools slightly, encouraging the next winter's snow to settle more easily. As this pattern repeats across many years, the patches begin to expand. What was once only a small remnant of winter becomes a wider blanket that reaches across valleys, plateaus, and northern hills. This growth does not happen through sudden leaps. It is a slow widening, a gradual thickening that only reveals its strength through time. Each additional layer of snow allows the ground below to remain just cold enough to welcome the next snowfall. The cycle becomes self-reinforcing. More snow reflects more sunlight. More reflection cools the air. Cooler air allows more snow to survive. What began as a fragile patch can eventually grow into a steady field of white, then into the early roots of a glacier. Once the land remains bright for long enough, the ice begins to shape itself. Snow compresses under its own weight, forming crystal layers that slowly turn into solid ice. That ice spreads outward like a frozen tide, moving with deep patience. A glacier does not rush. It advances by inches each year, or less, but over tens of thousands of years those inches add up. The landscape changes under its presence. Stones are carried away, valleys widen, and rivers are forced into new paths. As the ice expands, the albedo effect grows stronger. Large ice sheets reflect far more sunlight than scattered snow. This reflection influences the temperature not only of the land beneath the ice, but of the atmosphere above. Cold air spreads outward, sinking over forests, grasslands, and coastlines that once felt warmer. Even the oceans are touched by this cooling, their surfaces chilled by winds that carry the imprint of distant ice. there comes a point in some cycles when the effect deepens into something that feels almost unstoppable. This is what scientists call runaway cooling. It occurs when the growth of ice strengthens the effect so much that the climate begins to cool faster than it can warm. The balance tips decisively toward ice buildup. Summers become too weak to melt the year's snow. Winters add new layers more quickly than the sun can erase them. Ice sheets that were once small and scattered begin to grow into massive expanses that stretch across continents. During these periods, Earth enters a phase of long, slow cooling. Sea levels fall as more water becomes locked in ice. Winds shift as temperature differences between the poles and the equator grow sharper. Storms follow new paths. Ecosystems reorganize as plants and animals adapt to a world that is gradually losing its warmth. None of this happens swiftly. It unfolds through centuries and millennia, so slowly that no single lifetime would ever notice the turning, yet the planet's face changes all the same. Runaway cooling does not mean the world becomes uninhabitable. Life continues, adjusting to the new environment, just as it has done countless times before. Great animals roam the cold plains. Human ancestors find new paths through the altered landscapes. Forests shrink in some regions and expand in others. Lakes form where ice blocks river flow, and vast grasslands open where seas once stood. Eventually, the cycle shifts again. Other forces begin to counter the cooling. The planet moves along its orbital path. The tilt changes, the wobble turns. Together, these motions begin to weaken the albedo effect. Summers regain enough strength to melt the bright surface. Ice retreats, and the land underneath is revealed once more. But during the long cold phases, the albedo feedback remains one of the most influential forces in the climate system. It transforms small, surviving patches of snow into the great ice sheets that define Earth's repeated journey through ages of cold. In the brightness of ice, the planet finds one of its most powerful climatic levers, a reminder that even something as gentle as reflected sunlight can guide the fate of worlds. As the great sheets of ice grow and the brightness of their surfaces cools the air above, another influence moves quietly through Earth's long climate story. It is not a force that drives the beginning of an ice age, but one that strengthens its hold once the cold has begun. This influence is carbon dioxide, a simple molecule with a complex role in shaping the warmth of the planet. Its presence in the atmosphere is essential for life, yet its abundance shifts with the rhythms of Earth's changing climate. To understand how ice ages deepen, we must look at how carbon dioxide lingers, rises, and falls in response to the world around it. Though it is common to think of carbon dioxide as a cause of warming or cooling, in the cycles of the ancient ice ages, it behaves more like a responder. Temperature moves first, and carbon dioxide follows. This relationship becomes clear when scientists study the frozen air trapped deep within the ice of Antarctica and Greenland. Layer by layer, these bubbles show that temperatures began to fall long before carbon dioxide reached its lowest levels. The initial cooling came from changes in Earth's orbit, tilt and wobble, along with the brightness of expanding snow. Only after the world began to cool did carbon dioxide levels drift downward, deepening the chill that was already underway. The reason for this lies in the oceans, which hold far more carbon than the atmosphere ever could. The sea acts as a vast reservoir, able to absorb carbon when the world cools and release it when the world warms. This exchange happens through many subtle paths. Cold water absorbs gases more readily than warm water, so when Earth begins to cool, the surface layers of the ocean draw in more carbon dioxide from the air. Over centuries, the slow exchange lowers the amount of carbon dioxide in the atmosphere, and with fewer greenhouse gases surrounding the Earth, heat escapes more easily into space. The deep ocean plays a role as well. As surface waters cool and grow denser, they sink, carrying absorbed carbon downward into the quiet dark. This movement helps store carbon away from the atmosphere for long stretches of time. Upwelling currents in other regions may slow or shift, reducing the return of carbon to the surface. The balance between absorption and release begins to lean heavily towards storage. Each small change in circulation can influence how much carbon remains in the air and how much sinks into the depths. Land also responds to cooling in ways that influence carbon. Vegetation grows more slowly in colder climates. Plants take in less carbon from the atmosphere, and soils hold more of what would otherwise cycle back into the air. Dust storms, more common during glacial times, carry nutrients into the oceans that encourage the growth of tiny marine organisms. These organisms use carbon to build their structures, then sink to the seafloor when they die, carrying their carbon with them. Over many thousands of years, these quiet transfers help reduce the atmosphere's supply of carbon dioxide even further. Once carbon dioxide levels fall, the effect on climate is gentle but persistent. Greenhouse gases trap heat that would otherwise escape into the vast reach of space. With less carbon dioxide present, the air holds less of this warmth. Temperatures fall slightly more. Snow that survived the summer becomes more secure. Ice sheets gain a little more ground. The cooling and the carbon drawdown amplify one another, creating a loop that strengthens through time. Cooling leads to lower carbon dioxide. Lower carbon dioxide leads to more cooling. The cycle continues, adding depth to the ice age that has already begun. This feedback loop does not act with sudden force. It is patient and steady, much like the growth of the ice itself. No single season or year marks a turning point. Instead, the influence of carbon dioxide builds over centuries, gradually carrying the world deeper into glacial conditions. It is a quiet companion to the larger changes driven by Earth's orbit and the brightness of snow. Together, these forces shape the cold expanses that once spread across continents and lowered sea levels around the world. It is worth remembering that carbon dioxide does not fall on its own. It responds to the shifting climate, echoing the changes that the planet is already experiencing. In warm periods, the oceans release stored carbon as their waters heat and expand. Plants grow more quickly, returning carbon to the air. The world breathes in a rhythm shaped by temperature, sunlight, and ice. During interglacials, carbon dioxide rises slowly, helping the warmth settle in. During glacial ages, it falls, helping the cold deepen. Through this long pattern, carbon dioxide acts as a gentle amplifier. It does not begin the ice ages, but once they have taken hold, it supports their growth and helps maintain their strength. As the world cools, as snow lingers, and as ice stretches across northern lands, the atmosphere grows thinner in its ability to hold warmth. The planet settles into a quiet stillness until the orbital rhythms shift again, guiding the climate once more toward light and thaw. In this way, carbon dioxide joins the story, not as the spark that starts the cold, but as the soft echo that helps sustain it, shaping the depth and duration of the great winters that have come and gone through Earth's long memory. Beneath the shimmering surface of the oceans, far below the waves and drifting currents we see from shore, there is a deeper movement at work. It is patient and steady, so slow that an entire lifetime is only a moment in its journey. Yet this slow movement carries heat from one end of the planet to the other. It shapes storms, guides seasons, and helps decide whether the world leans toward warmth or cold. Scientists often call this flow the global ocean conveyor belt, a soft name for something immense, a system driven by differences in temperature and saltiness that gently pull water across the great basins of the world. To imagine this conveyor, picture warm surface waters traveling northward, carried by winds that sweep across the Atlantic. As the water moves, it releases its warmth to the air, softening winters in places like northern Europe. The water cools as it travels, and grows more dense. At the far northern reaches of the ocean, near the edge of the Arctic, it becomes heavy enough to sink. This sinking water slides downward into the deep, forming a slow river in the darkness that glides south again beneath the surface. From there, the journey continues through the deep Atlantic, around the southern oceans, and eventually into waters near the Indian and Pacific basins. After a long wandering path, parts of it rise again, warmed by sunlight, and the flow continues. This is thermohaline circulation, a term that speaks to temperature and salt. Warm water is lighter than cold water. Saltier water is heavier than fresher water. These small differences guide the deep pulse of the ocean. When cold and salty water forms at the surface, it sinks and drives the conveyor. When water becomes fresh from melting ice or heavy rainfall, it can disrupt the movement. During the ancient ice ages, the conveyor belt played a quiet but powerful role in shaping climate. When the world cooled, the formation of cold and dense water in the north became stronger. More sinking occurred, pulling warm water more quickly from lower latitudes into the high northern seas. This carried warmth northward, even during times when the planet was growing colder overall. The journey of the conveyor added complexity to the way ice sheets grew and retreated, creating pockets of relative warmth in one region and deeper chill in another. Yet the system is sensitive. Even small changes in fresh water can shift the flow. When large ice sheets begin to melt, they release enormous amounts of fresh water into the ocean. Fresh water is lighter than salty water, which makes it harder for the surface layers to sink. If enough fresh water enters the northern seas at once, the sinking that drives the conveyor can weaken or in some cases nearly stop. When that happens, heat is no longer carried northward in the same way. Winters in the high latitudes deepen, sea ice spreads more readily, storm patterns shift as energy moves differently through the atmosphere. Scientists have found evidence of this in layers of ancient sediments and deep ocean records. During some periods of rapid ice melt, the circulation slowed dramatically. In the North Atlantic, cold conditions strengthened even as parts of the world were warming. In other times, the circulation sped up, drawing warmth quickly northward and melting ice more rapidly. These shifts were not uniform across the globe. They created swirling patterns of climate that left fingerprints in pollen grains, ocean shells, and river sediments. The past shows that the ocean's slow and gentle conveyor can shape entire regions in ways that stretch far beyond its quiet surface. The conveyor also influences the great belts of rain that wrap around the equator. Warm water evaporates easily, filling the air with moisture. This moisture becomes the fuel for monsoons and tropical storms. When the conveyor shifts, the warm pools of water that feed these systems shift as well. A slight redirection of currents can alter rainfall patterns across continents. Lakes fill or shrink, forests expand or contract, droughts appear in places where rainfall once felt steady. Farther south, near Antarctica, the conveyor belt interacts with some of the coldest and windiest regions on Earth. Deep waters rising from below bring nutrients to the surface, feeding plankton that become the foundation of the food web. These upwelling zones help regulate the exchange of carbon between the ocean and the air. When circulation patterns weaken or strengthen, the amount of carbon stored in the deep ocean changes. This shift contributes to the rise or fall of carbon dioxide in the atmosphere, adding another layer to the long rhythm of ice ages. To picture the influence of the conveyor, imagine placing a hand over a candle. The warmth rises in a small, predictable stream. Now imagine spreading that warmth across entire oceans, carried gently by vast rivers of water. The conveyor is the candle's rise on a planetary scale, moving heat from equator to pole, from surface to depth, from century to century. Without it, the world's climate would be far harsher. Winter storms would sharpen, Tropical rains would shift. The ice sheets of the past might have grown differently, and the warm periods between them may never have unfolded as they did. In the quiet pull of sinking water and the soft rise of deep currents, the ocean carries the memory of ancient winters and the seeds of future ones. It is a slow and steady hand guiding the balance of warmth across the earth, shaping the landscapes that life has known for countless generations. As Earth settles deeper into the long quiet of an ice age, the world changes in ways that are not always obvious at first glance. The cold reaches outward from the high latitudes, shaping the growth of ice and the rhythm of the seasons. Yet far from the glaciers, another transformation unfolds. It begins with the drying of distant lands, the shifting of winds, and the soft motion of airborne grains that drift across continents and seas. This is the story of dust, a simple material that becomes unexpectedly powerful when the world grows cold. During glacial times, many regions become drier. The cooling of the ocean slows evaporation, and the air carries less moisture to distant soils. Grasslands that were once thick with life thin into sparse plains. Deserts expand across wide stretches of Africa, Asia, and the Americas. Rivers shrink or change their courses. Bare ground becomes exposed to the wind, and storms sweep across the landscape more easily than they do in warmer periods. Each gust lifts countless grains of silt and fine sediment into the sky, carrying them far beyond their place of origin. These dust storms, though subtle in the moment, become frequent enough to leave their mark in the geological record. Layers of wind-blown sediment accumulate across valleys, plateaus, and even polar regions. When scientists examine deep ice cores, they find distinct bands of fine dust that form during the coldest phases of past ice ages. Each band is a quiet reminder that the world was not only frozen, but also dry and windy, and that the atmosphere carried vast amounts of material from the land into the sea. It may seem surprising that dust, something so small and fragile, could influence the global climate, but hidden within these tiny particles is an element that shapes the life of the oceans: iron. Many parts of the sea are rich in nutrients like nitrogen and phosphorus, yet remain limited in their ability to support life because they lack enough iron. This iron acts as a spark for growth. Without it, much of the ocean remains quiet, its surface waters sparsely inhabited by the smallest organisms. When dust settles into the sea, it carries iron with it. The arrival of this iron awakens regions that were once limited. Plankton, the small drifting organisms that form the foundation of marine food webs, respond quickly. They grow, divide, and bloom in great numbers, forming vast patches of green that drift beneath the surface. These blooms do more than feed the creatures that swim above them. They draw carbon dioxide from the atmosphere, using it to build their tiny bodies. When the plankton die, some drift downward into the dark depths, carrying carbon with them. Over time, this process helps lower the amount of carbon dioxide in the air, reinforcing the cooling that the planet is already experiencing. This is iron fertilization, a process that unfolds naturally during glacial periods when dust storms become more common. In modern oceans, certain regions are known as high nutrient, low chlorophyll zones, places where the water contains plenty of the materials needed for life but lacks iron. During ice ages, these regions receive enough iron-rich dust to transform them. They become more productive, turning sunlight and carbon into living tissue at a rate much higher than during warmer times. The influence of iron fertilization reaches far beyond the surface. The burial of carbon-rich plankton on the seafloor removes carbon dioxide from the atmosphere for thousands or even millions of years. This deep storage strengthens the cooling that began with shifts in sunlight and the growth of snow. The atmosphere becomes thinner in greenhouse gases. The cold deepens and the ice advances further across the northern lands. In this way, dust becomes a quiet participant in the climate system. It does not drive the initial cooling, does not reshape continents or alter Earth's orbit. Instead, it acts as a subtle amplifier, arriving at the right moment to tip the balance even more toward cold. Its journey from desert to ocean shows how deeply connected Earth's systems are. Dry landscapes influence faraway seas. Tiny particles shape the breadth of the atmosphere. The smallest details help guide the largest transformations. Imagine standing at the edge of a glacial plain during a cold age. The air is sharp and dry. Wind stirs the surface of the land, carrying with it the remains of long weathered stones and ancient soils. These grains drift upward, join the clouds, and travel across the open sky. Days later, they fall over distant waters, disappearing into the surface as quietly as they rose. Beneath the waves, life responds, blooming into patterns that pull carbon from the air and store it in the deep. Through this simple path, dust becomes an unexpected shaper of climate. It turns the dryness of cold ages into nourishment for the sea. It deepens the cooling already underway, and in doing so, it becomes another thread in the long and delicate tapestry of Earth's repeating rhythm, linking distant deserts with the quiet breath of the oceans. As we follow the long path of Earth's changing climate, a pattern begins to stand out, steady and unmistakable. Ice ages rise and fall in cycles that last roughly 100,000 years, a rhythm carved clearly into ocean sediments and deep ice. Yet when scientists look toward the skies, at the slow stretching of Earth's orbit that repeats on a similar timescale, the connection feels strangely out of tune. The match is close but not convincing, like two melodies that follow the same beat, yet still drift apart. This mystery, known as the 100,000-year problem, sits at the center of Earth's frozen history. For much of the planet's past few million years, the cycle has repeated with remarkable consistency. Every 100,000 years or so, ice sheets grow across the northern continents, reach their widest extent, and then retreat again. The cycle defines the shape of Earth's recent climate, guiding the rise and fall of sea levels, altering landscapes, and shaping the migrations of early humans and animals. But when researchers trace the trigger behind this rhythm, they find something puzzling. The orbital change that repeats every 100,000 years, the stretching of Earth's path around the sun, is real, yet its influence on sunlight is surprisingly small. It does not seem strong enough to carve whole continents beneath ice. To understand the puzzle, we take a quiet step backward in time, beyond the last few cycles, and into an earlier world. Before roughly 1 million years ago, Earth's ice ages followed a different pattern. They came and went on a cycle closer to 41,000 years, a rhythm that matched the changes in Earth's tilt. This earlier alignment made much more sense. The tilt of the planet has a strong influence on the strength of the seasons. When the tilt increases, summers grow warmer and winters colder. When the tilt decreases, seasons soften. These differences directly affect whether snow survives summer in the far north. A 41,000-year cycle fits neatly with the physics of melting and freezing. So why did Earth shift from a gentle 41,000-year pattern to the deeper, longer pulse of 100,000 years? Why did the climate begin to follow a cycle that appears weaker in its effect and harder to explain? To explore this, scientists compare the record of Earth's orbit with the story written in the climate archives. In deep sea cores, they see temperature changes that rise and fall in ways that closely match the expansion and retreat of ice. In ice cores from the poles, they see layers of trapped air that show how carbon dioxide followed the same long beat. When these records are placed alongside the variations in Earth's orbit, the 100,000-year cycle stands out. It repeats again and again, even though the associated change in sunlight is gentle. Something in Earth's climate system must be amplifying the orbital rhythm, turning a small nudge into a large transformation. One leading idea is that the ice sheets themselves became different over time. As the planet cooled slowly through the early Pleistocene, ice sheets may have grown thicker and more deeply rooted in the land. Thick ice behaves differently from thin ice. It becomes more resistant to melting. It responds more slowly to seasonal warmth. It grows high enough to interact with the atmosphere in new ways, altering winds and moisture. Once ice sheets reached a certain size, they may have begun to follow the longer, weaker pacing of Earth's eccentric orbit rather than the tilt of the axis. This would explain why the climate shifted toward the 100,000-year rhythm, even though eccentricity offers only a small change in direct sunlight. Another idea suggests that the ocean played a deeper role. Over long periods, deep ocean circulation can store or release vast amounts of carbon, altering the planet's greenhouse effect. If the oceans gradually changed their circulation patterns around 1 million years ago, perhaps through tectonic shifts or changes in sea ice, they might have begun to amplify small orbital variations more strongly. A slight change in sunlight could then trigger a larger change in carbon and in turn a larger change in climate. Some researchers propose that the erosion of bedrock beneath the great northern ice sheets played a part. As ice thickened over hundreds of thousands of years, it ground down the land beneath. This erosion may have lowered the foundations of the ice sheets, making them more stable. Stable ice is harder to melt, encouraging cycles that grow deeper before they collapse. In this view, Earth's glacial rhythm lengthened because its ice sheets needed more time to reach the point where they would finally break apart. There are also suggestions that multiple factors worked together, forming a kind of resonance in Earth's climate system. The tilt continued its 41,000-year influence, but the ice sheets may have responded only during certain alignments with the orbit and the wobble. Over time, the climate may have fallen into a pattern where the 100,000-year cycle acted as a simple summary of a more complex interaction. No single explanation has been accepted fully. Instead, the 100,000-year cycle appears to be a product of many intertwined forces. The orbit provides the timing, the ice sheets provide the sensitivity, the oceans provide the amplification, and Earth as a whole responds in a way that feels both delicate and immense. In this way, the odd timing of the ice ages becomes one of the most intriguing mysteries of the planet's deep past, a reminder that even when we see a clear rhythm in nature, the reasons behind it may lie far beneath the surface, shaped by countless interactions across land, sea, and sky. As we wander deeper into Earth's long memory, we reach a moment when the rhythm of the planet's ice ages changed in a profound and quiet way. It happened roughly 1 million years ago, during a time scientists now call the mid-pleistocene transition. Before this turning point, Earth's great winters rose and fell on a steady beat of about 41,000 years. Then, almost as if the planet paused, listened, and chose a slower rhythm, the cycle lengthened to the 100,000-year pattern we see carved so clearly into ice and ocean today. What caused this shift is still being pieced together, but scientists have uncovered enough clues to show that something deep within the Earth system was quietly reshaping the pace of the world. To understand this moment, it helps to imagine the planet as it was before the transition. The ice sheets of the earlier Pleistocene were impressive, but not as massive as those of later times. They formed, expanded, and melted on a shorter rhythm that matched changes in Earth's tilt. These earlier cycles were gentler, like breaths that never quite reached the deepest sigh. Ice would grow across the northern lands, then retreat again before it could anchor itself fully into the continents beneath it. But around 1 million years ago, something changed. The ice sheets began to grow thicker, taller, and more deeply rooted in the land. they no longer melted completely during the warm phases. Instead, each glacial period left behind a little more ice than the one before. Over time, this allowed the ice sheets to build a greater foundation, much like a tree that grows wider rings with each quiet year. Once the ice reached a certain size and stability, the climate could no longer return to its earlier, faster cycle. The world slipped into a new rhythm that was slower and deeper. One idea for why this happened lies in the bedrock beneath the ice. As the earlier ice sheets formed and melted repeatedly, they scraped away at the land, carving valleys and grinding mountainsides into fine sediment. Each cycle of scraping removed more of the soft material beneath the ice and exposed harder, deeper rock layers. When the ice grew again, it anchored itself onto this firmer foundation. Thick ice tends to be more stable when it rests on solid ground. It melts more slowly, moves more steadily, and can survive warmer summers that would have cleared thinner ice away. In this view, the mid-Pleistocene transition was driven not by changes in sunlight, but by the slow reshaping of the continents beneath the ice. The ice sheets learned, in a sense, how to build themselves more firmly with each cycle. The land guided the ice, and the ice reshaped the land until the system reached a point where it no longer responded to the shorter tilt cycle. Once anchored to deeper bedrock, the ice sheets could withstand the warmer phases for longer periods, shifting the climate into a pattern where it took tens of thousands of years to fully melt them again. Another idea centers on the grounding lines of ice sheets, the places where thick ice meets the bedrock below sea level. When glaciers extend over coastal shelves, the grounding line marks the transition between ice resting on land and ice floating on water. If the ice sits on land that slopes downward inland, the grounding line can retreat rapidly once melting begins. But if the land slopes upward, or if erosion creates a more gently rising surface, the grounding line may become more stable. Around 1 million years ago, changes in bedrock topography may have created conditions that made the grounding of ice sheets more secure. This allowed ice to grow larger and persist for longer intervals. There are other possibilities. Some scientists think the world gradually cooled over millions of years, lowering global temperatures enough for ice sheets to reach a new size threshold. Others suggest the deep ocean circulation changed, storing carbon in different ways and lowering atmospheric carbon dioxide just enough to support larger ice sheets. Some propose that the interaction between sunlight and ice reached a new balance that favored longer glacial periods. And it may be that the transition was not caused by a single factor at all, but by several influences working quietly together. What is clear is that once the world passed this threshold, the Ice Age rhythm changed. The earlier pattern, driven strongly by the tilt of the Earth, faded into the background. A new cycle emerged, paced by the slow stretching of Earth's orbit and amplified by the growing strength and stability of the ice sheets themselves. From that point on, the planet's climate followed a slower and deeper rhythm, one that would guide the formation of the vast ice sheets that shaped the landscapes, coastlines, and ecosystems of the more recent Pleistocene. The mid-Pleistocene transition marks a moment when Earth's climate system shifted gears, slipping into a mode that allowed ice to grow larger, last longer, and reshape the world more profoundly. It was not a sudden change, but a long, quiet turning that unfolded over hundreds of thousands of years. Layer by layer, ice and bedrock came into a new balance, and the planet entered the long heartbeat of the 100,000-year cycle that continues to echo through its frozen history. As our story drifts toward the far southern edge of the world, the landscape changes into something quiet and immense. Antarctica sits wrapped in cold, far removed from the shifting forests and plains that once surrounded the northern ice sheets. It is a world of stillness, a white plateau lifted high above sea level, crowned with some of the thickest ice on Earth. Its isolation gives it a different rhythm from the north, yet it remains deeply connected to the planet's long cycles of cold and warmth. The Antarctic ice sheet is one of the most stable features in Earth's climate system. While northern ice sheets advanced and retreated many times over the past few million years, the southern ice has persisted in its frozen loneliness. Even during the warm phases between ice ages, Antarctica kept much of its ice. The reason lies partly in its geography. The continent sits squarely over the South Pole, surrounded not by sprawling land, but by a vast ring of ocean. High winds, cold air, and the distance from sunlit latitudes help preserve the cold that settles over its high interior. The ice here is ancient. Some layers of the East Antarctic ice sheet are more than 1 million years old. They formed long before the mid-pleistocene transition shifted the rhythm of global ice ages. This long-lived ice does not respond quickly to changes in sunlight or seasons. It behaves like a slow heart, beating on timescales that stretch beyond the familiar rises and falls of northern glaciers. Yet the stillness is not complete. Antarctica has its own ways of speaking with the rest of the planet. One of those ways is through the circumpolar currents, the powerful loops of water that race around the continent. These currents are driven by the strong westerly winds that sweep across the Southern Ocean. They circle Antarctica like a protective ring, preventing warm water from reaching the continent's edges. Because warm water cannot easily cross this barrier, Antarctica remains isolated from the heat carried by global ocean circulation. The currents act as a shield, preserving the cold of the southern ice sheet, even when other parts of the world grow milder. The circumpolar currents also help control the deep ocean. As they move, they stir waters from different depths, bringing cold water up to the surface and drawing surface waters downward. This exchange shapes the entire global conveyor belt that moves heat around the world. Much of the cold, deep water that flows northward begins its journey near Antarctica, where surface waters become so dense that they sink into the abyss. This sinking is part of what allows the ocean to carry heat from the equator toward higher latitudes. Because Antarctica plays such a large role in the deep ocean, it indirectly shapes the world's climate. When the ice sheet grows or melts, it affects sea level, ocean circulation, and even the storage of carbon in the deep ocean. Yet these shifts often unfold slowly. The southern ice does not respond as quickly to the planet's orbital rhythms as the northern ice does. Instead, it responds to changes that echo through the ocean over long stretches of time. The connection between the two hemispheres becomes clearer when we consider how northern triggers can influence southern ice. When northern ice sheets begin to grow, they cool the atmosphere and shift global patterns of moisture and wind. The oceans respond by changing their circulation, and these changes travel across the globe. Over thousands of years, the altered currents can bring slightly colder waters to the edge of Antarctica. These cooler waters can encourage sea ice to expand and help parts of the continental ice sheet thicken. During times of rapid northern melting, the influence moves in the opposite direction. Fresh water released from the northern ice disrupts the sinking of dense water in the North Atlantic, slowing the conveyor belt. When this happens, less warm water moves toward the Southern Ocean. The reduction in heat transport can cause the waters around Antarctica to cool, even though the melting event began thousands of miles away. In this sense, the southern ice can grow stronger even when the north is losing ice. The planet behaves like a seesaw, its climate tilting gently as changes in one hemisphere echo through the other. Antarctica also contributes its own voice to the conversation. Its vast expanse of bright ice reflects sunlight into space, reinforcing the planet's overall cooling. Its winds carry sea ice outward across the Southern Ocean, forming a thin but extensive shield that cools the waters beneath. When this sea ice expands, It increases the formation of cold, dense water that sinks to the ocean floor. This sinking transports carbon-rich water to the deep ocean, helping to lower atmospheric carbon dioxide and deepen global cooling. Thus, even though Antarctica does not react quickly, it can amplify changes that originate far beyond its shores. To stand at the edge of Antarctica, even in imagination, is to see a place where silence becomes a kind of strength. The ice stretches endlessly, carved by winds that have circled the globe without interruption. The sea beneath the cliffs of ice churns with deep water that has not touched the surface for centuries. The circumpolar currents race past, carrying the memory of warm and cold ages alike. This southern world feels distant, yet its influence reaches far. It is the anchor that steadies Earth's climate, the place where cold gathers and spreads. Even as the northern hemisphere shapes the beginning of ice ages, Antarctica shapes their depth. Together, they weave the alternating patterns of warmth and cold that have guided Earth for more than 1 million years. As Earth moves through its long cycles of ice and warmth, there is a quiet tension that stretches across the planet from north to south. It is not a struggle of force, but a gentle competition shaped by sunlight. Each hemisphere takes turns leaning a little closer to the sun during the part of Earth's orbit when it matters most. Over thousands of years, this exchange guides the balance of warmth, shaping when ice grows, when it melts, and how the climate tilts toward one direction or the other. Scientists sometimes describe this as a tug of war, though the movement is soft, patient, and far too slow for any single lifetime to witness. This tug of war is driven by precession, the slow wobble that turns Earth's axis through the sky. Over roughly 26,000 years, the axis traces a slow circle. As it does, the orientation of the hemispheres shifts. At one point in the cycle, the northern hemisphere faces the sun more directly during the time of year, when Earth is closest to the sun in its orbit. Thousands of years later, the wobble continues, and the southern hemisphere takes that position instead. The strength of sunlight that reaches each hemisphere during its summer changes with this long turning. When a hemisphere receives stronger summer sunlight, its warm season becomes more intense, snow melts more quickly, ice retreats more easily, seas warm a little faster beneath the longer days. Meanwhile, the opposite hemisphere experiences a gentler summer, one where the sun keeps a softer angle and the warmth settles more quietly onto the land. Then, as the wobble continues its slow sweep, the roles reverse. This alternating pattern seems simple at first glance, like a cosmic pendulum that shifts warmth from one side of the planet to the other. Yet Earth does not respond evenly. The hemispheres are not twins. One holds far more power in guiding the rhythm of the ice ages. That power belongs to the northern hemisphere. The reason is hidden in the shapes of the continents. The north holds large stretches of land, from the wide plains of Eurasia to the forests of Canada, the mountains of Alaska, and the tundra surrounding the Arctic. Land responds quickly to changes in sunlight. It warms easily when the sun grows strong, and cools just as easily when winter takes hold. Winter snow can settle widely across these open stretches. In cooler summers, snow can linger across high plateaus and northern slopes. When the planets tilt, wobble, and orbital stretch align in a way that favors cooler northern summers. The land offers broad surfaces on which ice can take root. The southern hemisphere is shaped very differently. Much of it is dominated by ocean. Water resists temperature changes. It absorbs heat slowly and releases it slowly, smoothing out the seasons and softening the extremes that drive ice growth. Even though Antarctica sits firmly in the south, its isolation behind the circumpolar current makes its climate follow its own deep rhythm. The great southern oceans surround it like a shield, preventing the immediate buildup of ice across nearby continents. The result is that southern summers and winters do not shift the global balance as strongly as those of the north. Because of this imbalance, the tug of war between the hemispheres is not equal. When northern summers weaken, even slightly, the effect on climate can be profound. Snow lingers, ice gains a foothold, bright surfaces reflect sunlight and deepen the cooling. Ocean currents adjust, carrying colder waters along different paths. Atmospheric patterns shift. A cascade begins that can eventually draw the entire world into deeper cold. When southern summers weaken, the effects remain more contained, buffered by the breadth of the southern seas. Even within this imbalance, the tug of war continues its quiet cycle. Imagine standing at the edge of a northern coastline during a time when the wobble favors strong northern summers. The days widen, the land warms quickly, rivers swell with meltwater, snow retreats deep into the mountains. Then imagine the same place thousands of years later during a different phase. The sun's path across the sky holds a cooler glow. Summers feel shorter. Snow that once melted in early spring remains through midsummer. Ice creeps outward in cautious steps. The dates themselves slip past unnoticed by any one lifetime, yet the world below changes profoundly. In the south, the opposite pattern unfolds. While the northern hemisphere experiences strong summers, the south enjoys gentler warmth. Antarctic sea ice spreads more easily. Colder air gathers over the southern ocean. Then, as the wobble continues, the southern hemisphere receives brighter summer light. Ice retreats at the edges of the Antarctic plateau. The oceans warm softly beneath longer daylight hours. The north follows with milder warmth of its own. This push and pull shapes the long memory of Earth's climate. When the tug between the hemispheres aligns with the stretching of Earth's orbit and the changing tilt of its axis, the world moves into a phase where ice sheets grow for tens of thousands of years. When the alignment favors stronger northern summers, the ice retreats, seas rise, and a warm interglacial settles in. The tug of war is not a contest with winners or losers. It is a balance, a conversation between land and ocean, light and shadow, north and south. Its slow shifts help decide the rhythm of the ice ages, weaving together the many influences that shape the deep history of Earth's changing climate. As Earth moves through its long cycles of ice and warmth, most of the forces guiding these shifts unfold slowly. They follow the pace of continents, oceans, and the great orbital rhythms that stretch across tens of thousands of years. Yet scattered throughout this gentle story are brief moments of sudden change, moments when the planet's calm surface breaks open and releases something far more immediate. These moments come from volcanoes, the deep breath of Earth's interior rising to the surface in a plume of ash, heat, and gas. A volcanic eruption can transform the sky in a matter of hours. Ash climbs into the air, carried upward by columns of rising heat. If the eruption is strong enough, this ash can reach the stratosphere, far above the clouds and the weather most of us know. Once there, it drifts across continents, spreading into a thin veil that circles the globe. The ash and tiny droplets of sulfur-rich aerosols reflect sunlight back into space. The world beneath becomes slightly darker, slightly cooler, and slightly quieter. These cooling moments can last for months or even a few years, leaving subtle marks in climate records and tree rings. Throughout history, large eruptions have caused noticeable dips in temperature. Some eruptions cooled the world enough to alter harvests and seasons. Lakes froze early, winters lingered. Skies took on a muted glow as sunlight filtered through the thin haze of airborne particles. Yet, as dramatic as these moments can be, they never last long. The ash settles, the aerosols break down, winds disperse the veil of particles until the familiar blue sky returns. The cooling fades, and the climate returns to the path it was already following. Volcanoes can also warm the planet, though in a slower and more subtle way. Along with ash and aerosols, eruptions release gases from deep within Earth's interior, including carbon dioxide. This gas remains in the atmosphere far longer than volcanic ash. Over geological time, volcanoes contribute a slow and steady supply of carbon dioxide that helps maintain the planet's overall warmth. Without this long term release, Earth would gradually lose carbon to the rocks and oceans, becoming far colder than the world we know. Volcanoes, in this sense, help sustain life by replenishing the atmospheric carbon that weathering and biological processes constantly draw down. Yet, even this warming influence is gentle. The amount of carbon dioxide released by volcanoes each year is small compared to the amount cycled between the oceans, atmosphere, and living things. Most eruptions release far less carbon than the ocean absorbs or emits over similar periods. Only over millions of years does volcanic carbon dioxide accumulate enough to shift Earth's climate significantly. It is a slow voice, one that shapes the background warmth of the planet, but does not determine the timing of glacial cycles. This is why volcanoes, though powerful, cannot set the rhythm of the ice ages. Their influence is too short lived or too evenly spread across time to create the repeating pattern of cooling and thawing that defines Earth's long climate memory. An eruption may create a brief cooling spike that softens the summer warmth of a single year, but it cannot hold back the sun or alter the tilt of Earth's axis. It cannot reshape ocean circulation on its own or build the slow feedbacks that guide ice sheet growth. Even chains of eruptions, occurring across decades, cannot match the influence of orbital rhythms that unfold across thousands of years. The growth of ice sheets requires centuries of snow accumulation and subtle changes in summer sunlight. The deep ocean needs time to shift its currents. Carbon drawn down by plankton blooms or stored in cold waters requires long, quiet processes to build. Volcanoes, by contrast, act in quick bursts. They speak in flashes rather than in the long sentences the climate understands. Still, volcanoes do play a delicate supporting role. When eruptions occur during a period of cooling, their ash clouds can help strengthen the downward trend. They can help snow survive an extra season. They can darken the sky enough to give ice a small advantage in its slow expansion. When eruptions occur during warming periods, the extra carbon they release may soften the global descent into chill. These effects are small, but over many cycles, they leave faint traces in Earth's climate history. Imagine standing near a volcanic peak in a colder age. Snow rests along the slopes, but the summit trembles with deep movement. A sudden roar breaks through the quiet. Ash rises into the sky, illuminated by streaks of molten fire. The plume climbs higher and higher until it reaches the calm, dry air above the clouds. There, it spreads like a pale shadow across the sky. Days later, thousands of miles away, sunlight dims in places that have never seen the volcano itself. The world cools slightly, subtly, briefly. These moments remind us that Earth's climate is shaped by both slow and sudden forces. Volcanoes contribute their own flickers of change, flashes that ripple across months or years, but they do not conduct the larger symphony of ice ages. They offer brief interruptions, gentle nudges, and small adjustments to a story guided mainly by the planet's journey through space and the long patience of oceans, ice, and atmosphere. In this way, volcanoes stand as vivid but fleeting participants in the climate record. They leave dramatic marks, yet they cannot rewrite the rhythm. Their voice is strong, but momentary, woven into a story shaped by far quieter and older cycles that reach across the deep time of Earth. As we drift farther into the story of Earth's changing climate, it becomes natural to look upward, toward the great light that feeds the world with warmth. The sun, steady and ancient, appears constant from one day to the next. Its rising marks the rhythm of life, and its gentle light shapes seasons and sky. Yet when scientists study the sun carefully, they find that it is not entirely unchanging. Its brightness shifts slightly over centuries. Its magnetic breath waxes and wanes. Its surface blooms with dark sunspots that appear and fade like quiet freckles across its shining face. These changes are small. The sun's output varies by a tiny fraction of its total energy. Most of the time, these variations pass unnoticed by anyone standing on Earth's surface. Days feel the same, seasons unfold in familiar ways, but over longer stretches of time, the subtle changes in sunlight can influence climate in gentle and indirect ways. They never rewrite the story on their own, but they leave faint impressions that blend into the planet's greater rhythms. One way scientists observe solar variability is through the cycle of sunspots. These dark patches represent areas where the sun's magnetic field coils tightly and suppresses the flow of heat. When sunspots cluster, the sun becomes slightly more active. Paradoxically, this increased activity makes the sun shine a little brighter overall, because the bright regions surrounding the darker spots more than compensate for the shadows they cast. When sunspots are few, the sun's energy output softens. These cycles, which last about 11 years on average, ripple through Earth's upper atmosphere and can influence weather patterns in subtle ways. Beyond sunspots, there are longer and quieter shifts in the sun's behavior. Over centuries, periods of low activity can last long enough to create cool spells on Earth. The most well-known example is the time between the 16th and 18th centuries, when sunspot numbers dropped for an extended period. Temperatures dipped slightly during these centuries, and in some regions winters grew harsher and rivers froze more readily. These changes were real, yet they were gentle, almost like a faint shiver passing through the planet, rather than a deep transformation. Even at its most variable, the sun's changes are far too small to create or end an ice age. Ice ages require massive shifts in the balance of energy across the globe. They depend on patterns of sunlight that change at high latitudes in ways that influence snow survival, ice growth, and ocean circulation. These patterns are controlled by Earth's orbit, tilt, and wobble, not by the sun's internal cycles. No solar variation is strong enough to replace the slow, steady influence of these orbital rhythms. Imagine the difference between a small stone dropped into a lake and a rising tide that fills the entire shoreline. The stone creates ripples, delicate and temporary. The tide reshapes the land in ways that last for hours or days. Solar variability is the stone. The orbital cycles are the tide. Both matter, but only one is strong enough to guide Earth into the deep freeze of a glacial age. Still, the sun is not merely a bystander. As the planet grows cooler or warmer for reasons rooted in its orbit, the sun's subtle changes can amplify the direction of the shift. During times when the sun grows slightly brighter, summers may become just warm enough to melt a little more snow at high latitudes. This warmth does not reverse the long trend of an ice age, but it can soften the edges of cooling or enhance warming during transitions between glacial and interglacial phases. In colder periods, when the sun's output dips, its influence can work quietly with the expanding ice. Cooler air encourages sea ice to stretch farther across the oceans. Snow becomes more likely to linger in regions where temperatures hover near the freezing point. Vegetation shifts slightly, altering the way the land reflects sunlight. These small nudges help the climate lean more fully into the cooling that has already begun. Solar variability also influences atmospheric patterns. Slight changes in solar output can alter the flow of high-altitude winds, shaping the paths of storms and shifting rainfall patterns. In some regions, this can create moments of increased dryness or periods of wetter seasons. These effects are small but real, and over centuries they blend into the climate record. Yet, even with these influences, the sun remains a secondary player in Earth's long climate cycles. It offers quiet adjustments rather than deep shifts. Its variations build on the foundation set by the planet's orbit and the complex feedbacks that shape the growth of ice. The sun adds subtle texture to the climate's long story, but it does not compose the main melody. Picture the sun as a gentle conductor, raising or lowering its baton ever so slightly, but the orchestra itself is driven by larger instruments. The tilt of Earth's axis, the stretching of its orbit, the wobble that turns its seasons, the oceans that carry heat across the globe, and the ice that brightens the world with its reflective surface all play far stronger roles in guiding climate through the ages. The sun follows their lead, illuminating the stage with light that shines nearly constant, yet never perfectly still. In this interplay between light and shadow, between stability and subtle change, the sun adds its own whisper to the evolving climate. It does not set the rhythm of the ice ages, but it shapes the atmosphere in quiet ways that echo through the centuries, blending into the great and patient story of Earth's shifting warmth and cold. As we move through the long arc of Earth's frozen history, it becomes clear that the growth of ice follows a slow and patient rhythm. Snow gathers, bright surfaces widen, oceans respond, carbon sinks quietly into the deep. Yet, just as the world settles into its coldest phases, another transformation begins beneath the stillness. Ice ages do not last forever, they end in moments that seem sudden when viewed through the lens of deep time, as if the planet releases a long held breath. To understand how these great winters come to a close, we return to the quiet machinery that helped create them. The cooling began with orbital shifts that softened northern summers, allowing snow to survive and ice to build. Feedbacks of brightness, carbon, and ocean circulation strengthened the cold. But the same orbital cycles that lead Earth into deep freeze eventually guide it back toward warmth. The cooling feedback loop breaks when summer sunlight over the northern latitudes grows strong enough to melt the snow that once lingered year after year. Northern ice sheets are fragile in their own way. Their survival depends on cold summers more than cold winters. Winters can be frigid, yet if a single summer grows warm enough, the delicate balance tips, sunlight begins to carve into the ice, softening its surface, letting meltwater spread across its top. Pools of liquid darken the snow, absorbing more heat, channels form and widen, rivers run through blue ice, flowing toward the sea. Once melting begins in earnest, the feedbacks that once cooled the world begin to reverse. This shift is not gradual in the way ice growth tends to be. Paleoclimate records reveal that the end of ice ages often unfolds in leaps. In layers of sediment preserved beneath the ocean floor, we see signs of rapid warming that took place over just a few centuries, and sometimes even within a single human lifetime. Temperature markers rise sharply, dust layers disappear, ocean chemistry changes as deep currents adjust to the new warmth. These rapid warming events show that once the tipping point is reached, Earth's climate reacts quickly. One of the most dramatic signs of an ending ice age is the collapse of ice shelves and the release of meltwater pulses into the seas. Ice shelves are the floating extensions of continental ice sheets. They act as quiet buttresses, slowing the flow of land-based ice into the ocean. When these shelves weaken, crack, or break apart, the grounded ice behind them can surge forward like a slow avalanche. In the distant past, enormous shelves spanning hundreds of miles fractured during warming periods. Their breakup allowed glaciers to accelerate, sending vast amounts of ice and fresh water into the ocean. These meltwater pulses are recorded in coral reefs and ocean sediments. They show moments when sea level rose not by inches over centuries, but by many feet in a surprisingly short time. In some periods, sea level appears to have risen by more than 10 feet within just a few hundred years, This rise reshaped coastlines, drowned low-lying plains, and flooded valleys that had been dry for tens of thousands of years. As the ocean absorbed the influx of fresh water, currents shifted, and the planet responded in ways that echoed through the atmosphere. Inside the ice sheets themselves, warming creates its own kind of momentum. Meltwater percolates downward through cracks and crevices. When it reaches the base of the ice, it lubricates the bedrock below, allowing entire sections of ice to slide more quickly. This process can speed the retreat of the ice sheet, making it more vulnerable to the next summer's warmth. The landscape beneath the ice also plays a role. Valleys carved during earlier glaciations can channel meltwater, guiding the collapse. Flat plains beneath thick ice can allow the glacier to detach from its base, speeding its disintegration. Ocean temperatures contribute to the process as well. Warm currents move toward the edges of collapsing ice sheets. Even a slight increase in water temperature can melt the underside of floating ice shelves from below, thinning them until they become unstable. When shelves collapse, they expose towering ice cliffs to the open ocean. These cliffs can shed ice in great slabs, adding to the rapid loss of mass and the rising of the seas. As the ice retreats, the Earth's surface begins to change its appearance. Darker land replaces bright snow. Forests expand into regions once covered in tundra. Lakes form in wide depressions carved by the ice. These new dark surfaces absorb more sunlight, warming the air above them. Vegetation spreads across the landscape, releasing moisture into the atmosphere. The planet begins to amplify its own warming. The cooling feedback loop has fully reversed. The atmosphere responds quickly to these changes. Winds adjust as temperature gradients shift. Storm tracks migrate. Moisture patterns reorganize themselves. Carbon that had been locked away in the deep ocean begins to rise to the surface as currents change. More carbon dioxide enters the air, adding warmth to a world already moving out of its deep freeze. In a sense, the climate system remembers warmth once it begins to return. By the time the ice sheets have retreated significantly, the transformation is complete. A warm interglacial begins, filled with forests, rivers, and expanding life. Seas settle into new shapes. The atmosphere becomes more humid. The sun shines on a world that feels open and generous once again. The end of an ice age is not a single moment, but a cascade. It begins with sunlight growing stronger over northern summers, then unfolds through melting, flowing, collapsing, and warming. It is the quiet unwinding of the long glacial grip, a return to warmth guided by the same ancient rhythms that once led Earth into cold. Through this slow turning, the planet breathes out, ready for the next chapter in its patient and endless cycle. When the last great sheets of ice retreat and the oceans rise to meet the new warmth, Earth enters a gentler chapter. These intervals of relative calm are the interglacials, short breaths of warmth that sit between the long inhales of glacial cold. They do not last long in the scale of deep time. Most stretch for about 10,000 to 20,000 years, brief flickers compared to the long winters that surround them. Yet within these bright windows, life reshapes itself in ways that echo for ages. To picture an interglacial, imagine the world moments after an ice age has loosened its grip. The air feels softer, the winds shift. Valleys that once held glaciers now carry clear rivers swollen with meltwater. Forests return slowly at first, then with determination, spreading across land that had been bare and frozen for tens of thousands of years. Grasslands green again, lakes fill. The Earth's surface darkens with soil and vegetation, absorbing sunlight and warming even further. This warmth builds a stability that allows plants and animals to flourish in forms impossible during deep freeze. Past interglacials reveal this pattern clearly. Sediment cores from ancient lakes and seabeds contain pollen from species that lived only in warmer climates. They show forests advancing northward, sometimes reaching places that today feel far too cold for such life. Coral reefs expanded during these warm times, growing upward towards sunlight as sea levels rose above the marks left by earlier glacial lows. In many regions, rivers carried greater flows, carving new paths across the warming land. These warm phases did not erase the memory of the ice that came before. Large lakes often lingered in basins carved by glaciers. Soil patterns still reflected the scouring of ancient ice sheets. Mountains carried fresh signs of erosion, their ridges sharpened or smoothed by the weight of the ice that once lay across them. Even the species that lived through these times carried adaptations shaped by the hardships of glacial environments. Interglacials were not a reset but a reprieve. In each interglacial, life took advantage of the open space. Animals moved into new habitats with eager curiosity. Great mammals roamed plains that had once been permafrost. Birds followed the spread of forests and wetlands. Plant communities reorganized themselves, forming dense woodlands in one region and wide meadows in another. Insects filled the warming air, flourishing in the restored seasons of growth. The world felt alive in a way that seemed to contrast sharply with the slow silence of the previous glacial cold. Earth's climate during past interglacials varied from one warm window to the next. Some were slightly warmer than today, with forests extending farther poleward. Others were cooler, their warmth moderated by the lingering influence of the oceans, but all were brief. The pace of the planet's orbit continued its slow turning, always guiding Earth toward the next deep winter. Interglacials were pauses, not endings, and the world never stayed in these warm phases for long. Today we live in one of these rare intervals, the Holocene, which began roughly 11,000 years ago when the last great ice sheets withdrew from North America and Eurasia. It is the warmth that allowed agriculture to take root, rivers to become centers of civilization, and coastlines to stabilize long enough for human communities to grow. Compared to previous interglacials, the Holocene sits comfortably within the range of natural variability. Temperatures have remained unusually stable across its span. Forests expanded, wetlands thrived. Species that lived on the edge of survival during the Ice Age found rich new homes. Yet even within this stability, the faint imprint of the old cycles remains. Studies of past warm periods show that each interglacial carries its own signature. Some lasted barely 10,000 years before ice returned. Others stretched closer to 20,000 years. Most followed familiar patterns of initial rapid warming, a short plateau of climatic stability, and then a slow decline in temperature as the northern summer sunlight weakened again. The Holocene has followed a similar path, beginning with rapid warming and then settling into a long period of gentle climatic calm. During these warm phases, ecosystems blossomed in extraordinary ways. Interspecies interactions became more complex. Forest canopies filled with life from top to bottom. Large herbivores shaped grasslands, and predators followed their migrations. Human ancestors, and later humans themselves, crossed newly opened routes that had been buried under ice for millennia. The warm climates offered food, water, and shelter in abundance, allowing population growth and the expansion of culture and community. Coral reefs, which struggle in cold waters, grew into bright underwater cities. Warm seas allowed them to stretch across tropical belts, creating ecosystems rich with fish, invertebrates, and plant life. In lakes and rivers, warm water supported growing networks of organisms. Freshwater environments thrived with algae, reeds, and the small animals that fed upon them. Interglacials were times of movement and expansion when species tested the outer edges of their ranges and found new places to thrive. The landscapes themselves adapted to these cycles. Soils developed in layers that reflected the warmth and the pulse of plants living and dying across thousands of years. Mountain slopes that once held glaciers now supported forests. River deltas grew wider. Coastal plains extended inland, shaped by the rising seas that followed the melting of ice sheets. Each interglacial ended gradually, but the strength of sunlight over northern summers held the key. When that sunlight weakened, the delicate balance began to tilt again towards snow that lingered, then accumulated, then spread. Forests retreated, grasslands shrank, sea levels fell as ice reclaimed water, and once again the long winter returned. In this cycle of warmth and cold, interglacials are the rare chapters where life stretches, breathes, and explores. They are short, gentle respites in the deep rhythm of Earth's glacial heart, times when the world sheds its ice and welcomes the flourishing of everything that depends on light, warmth, and open land. As the great winters tightened their grip on Earth, transforming continents into kingdoms of ice, life did not disappear. It shifted, adapted, endured. Across the long glacial nights, when cold air settled over plains for thousands of years, and ice sheets towered like frozen walls, plants and animals learned to survive in ways that still echo through their descendants. Even our own early ancestors walked through these harsh landscapes, shaped by the demands of a world where warmth was precious and food often scarce. Imagine standing on the northern plains at the height of a deep freeze. The land stretches wide and pale beneath a soft, muted sky. Winds flow over the ground with a steady patience, carrying fine snow that dances in thin spirals across the surface. Far in the distance, the edge of a continental ice sheet rises like a horizon made of stone, its cliffs glimmering blue beneath layers of compacted snow. Yet the land before it is not empty. In the cold, life forms a network of resilience. Our distant ancestors, members of the many human lineages that lived alongside the advancing ice, carried within them a quiet determination. They traveled across grasslands, river valleys, and forests, reshaped by the cold. Their survival depended on learning the rhythms of an unforgiving environment. Fire became more than warmth. It was shelter, protection, and a way to cook the tough and fibrous foods available in cold seasons. Clothing crafted from animal hides shielded their bodies from winds that could freeze exposed skin in minutes. Shelters took many forms. Some groups used caves, deep stone chambers carved long ago by rivers or shaped by slow erosion. Other groups built temporary homes from bones and hides, creating dome-like structures that held in heat through long winter nights. These people followed migrating herds, learned the behavior of large animals, and used every part of their prey. Their tools grew sharper, lighter, and more efficient. Stone blades, bone needles, and wooden spears became extensions of the body, shaped by necessity and passed down through generations. Alongside early humans roamed the great animals that defined the Ice Age. The woolly mammoth, towering and shaggy, moved across the plains in herds that could reshape the land beneath their heavy steps. Their long curved tusks helped them sweep aside snow to reach the grasses hidden below. Thick layers of fat insulated their bodies. Their fur, dense and layered, held warmth close, protecting them from wind and cold they had evolved to withstand. Mammoths were not simply large animals, they were woven into the fabric of Ice Age ecosystems, shaping plant growth, feeding predators, and providing essential resources for early humans who hunted them with courage and cooperation. Nearby, the cave lion stalked the glacial steppes. Larger than modern lions, it carried a strength adapted to open, cold landscapes. Its hunts took place across vast distances, guided by keen senses and the hunger that drove many Ice Age predators. Packs of dire wolves roamed the same regions, their bodies built for endurance. They followed herds, tracked scents for miles, and worked together to bring down prey many times their size. Other animals found strategies of their own. The woolly rhinoceros, wrapped in thick fur, grazed on the low shrubs and hardy grasses that survived the cold. Reindeer and musk oxen moved in shifting herds, their hooves and horns adapted to scraping snow away from hidden vegetation. Giant deer, with antlers stretching wider than a person is tall, navigated forests and open plains, feeding on whatever plants could grow in the brief bursts of summer warmth. Even small creatures adapted. Arctic hares grew coats so white they vanished into the snow. Lemmings carved tunnels beneath the surface, living in insulated chambers that stayed surprisingly warm compared to the freezing air above. Birds migrated across great distances, following narrow bands of livable climates where water remained open and food remained abundant enough to sustain them. Plant life found its own ways to endure. In the coldest regions, only mosses, grasses, and hardy shrubs could survive. Their roots reached through frozen soils to find the thin layers that thawed for only a few weeks each year. These plants formed the base of food chains that circled through small animals, then herbivores, and finally into the bodies of predators and scavengers. The simplicity of the vegetation did not weaken these ecosystems. Instead, it brought clarity. Every species relied on every other in tightly knit webs, each life woven into the next. The ice margin, where glaciers met open land, became one of the most dynamic environments on Earth. Meltwater carved rivers through frozen plains. Lakes formed where the ice retreated, leaving behind depressions filled with cold blue water. These boundary zones shifted with the seasons and with the slow advance or retreat of the ice sheets. Animals moved through these regions, drawn by fresh vegetation in summer and by the shelter of terrain shaped by the melting ice. Human ancestors also followed the changing edges, finding new routes as old ones closed beneath advancing glaciers. In warmer pockets far from the ice, forests persisted. Pine, spruce, and birch formed quiet sanctuaries where winters were cold but not crushing. These pockets of milder climate provided refuge for species that could not tolerate the harsher conditions of the open steppe. As glacial temperatures shifted, these refuges became the seeds from which new forests spread during the next interglacial, filling the land again with green. Life during the deep freezes was built on movement, adaptation, and patience. Species shifted their ranges, altered their diets, and used the landscape in ways that allowed them to endure the long cold. Humans learned to work together, building knowledge that would carry their descendants through countless future changes. Mammoths, lions, wolves, and birds shaped the land with their presence. Plants held on in small patches, waiting for the warmth that would eventually return. Through all of this, the world remained alive. Even in the coldest moments, ecosystems found ways to reorganize themselves, gathering along riverbanks, clustering near unfrozen springs, or spreading across vast plains that persisted between the ice sheets. Life did not merely survive the deep freezes, it evolved, adapted, and prepared itself for the next warm chapter of Earth's endless cycle. Beneath the quiet weight of the great ice sheets, hidden worlds lie in darkness. For thousands of years at a time, entire landscapes sleep under layers of frozen water that can rise miles above the buried ground. These hidden realms remain unseen until the ice retreats, yet they shape the way glaciers move, carve and sculpt the planet. To imagine this secret geography, we must step gently beneath the frozen surface and picture what lies below. Ice is not as still as it appears. Even when it stretches across a continent, it behaves like a slow-moving river. Under its own weight, it flows outward from its thickest center. The ice presses down on the land, pushing into valleys, sliding along plains, and grinding against mountains. Over thousands of years, This movement reshapes the terrain beneath. Bedrock that once formed solid cliffs softens under constant pressure, ridges narrow, valleys widen. The ice acts as a sculptor, carving the planet with the steady patience of deep time. One of the most striking effects of this pressure is the way ice sheets carve long, smooth valleys into the land. When ice fills an existing valley, it grinds against the rock walls, widening them into broad U-shaped troughs. These glacial valleys become some of the most recognizable features once the ice has melted away. They stretch across continents, silent reminders of the heavy ice that once lay upon them. Deep lakes often form at their bases, filling with meltwater that settles into the spaces carved by the glacier's slow passage. In other places, the ice scrapes across plains, smoothing the ground into gentle curves. It pushes soil and stone aside, gathering debris into long ridges that mark the edges of its advance. These ridges, known as moraines, outline the past boundaries of the ice. They remain long after the ice retreats, forming new landscapes that guide rivers, forests, and human settlements. Some moraines rise only a few feet, others grow large enough to resemble low mountain ranges, built entirely from the materials carried within the ice. Yet the deepest secrets lie in places where the ice sheets bury entire ancient worlds. Beneath the Greenland and Antarctic ice sheets, there are valleys deeper than the Grand Canyon. There are mountain ranges sharpened by erosion, river channels that once carried flowing water, and plains shaped by climates long vanished. Scientists discover these features through radar that travels through the ice and reflects from the rock below. These invisible maps reveal a hidden topography that existed long before the first snows began to fall on these lands. Some of the rivers buried beneath the ice sheets have not carried liquid water for more than 1 million years. Their channels remain preserved in perfect silence. In Antarctica, there are basins so deep that if the ice vanished entirely, vast lakes would appear in places where no drop of liquid water has existed since the continent froze. These hidden lakes still exist in pockets beneath the ice today. They lie under pressure sealed from the sky, surrounded by rock and ancient sediments. In complete darkness, some of them host tiny microbial worlds that survive through chemical reactions rather than sunlight. In other regions, mountain ranges stand beneath the ice like frozen guardians. Their peaks are buried and unseen, yet their shape influences the flow of the ice above. When the ice presses against a mountain ridge, it slows, splits, or accelerates depending on the terrain. The ice may carve deeply into one side while leaving the opposite slope untouched. These interactions between ice and mountain shape the ice sheet's movement over thousands of years. Glacial erosion can uncover rocks that formed hundreds of millions of years before the Ice Age began. When the ice retreats, it exposes these rocks to the open air for the first time since the ancient world that created them. Scientists walking across newly uncovered land after a glacier melts often find bedrock that has not been seen by sunlight since early Earth ecosystems thrived in shallow seas. The ice becomes a geologist's window into deep time, revealing stories carved into stone long before humans existed. As the ice sheets advance and retreat, they leave behind landscapes filled with unexpected complexity. In some places, deep depressions remain where the ice pressed the ground downward. When the weight lifts, the land slowly rises, a process known as isostatic rebound. This rise can continue for thousands of years after the ice has disappeared. Coastlines shift as land lifts from the sea. Ancient shorelines climb upward into hills. Islands merge with continents. Lakes shrink or drain entirely. The earth slowly breathes out the pressure that the ice once held. Other regions become networks of channels and ridges. When ice melts rapidly, it releases meltwater that flows beneath the glacier in powerful streams. These subglacial rivers carve tunnels through sediment and rock. When the ice retreats, the remaining channels form dry pathways called eskers. They run like long, winding trails across the landscape, tracing the routes of rivers that once flowed in complete darkness beneath a mile of ice. In this hidden world beneath the ice sheets, every feature tells a story of pressure, movement, and time. The ice does not merely cover the land, it becomes part of the land's shaping force, leaving its mark on every valley, ridge, and plain. When the ice finally retreats, it reveals a geography that feels both ancient and newly born, a landscape sculpted by forces far more patient than wind or rain. This unseen terrain, shaped through countless cycles of freezing and thawing, becomes the foundation of the world that emerges after the ice age's end. Forests will grow in its carved valleys. Rivers will follow the paths opened by ancient meltwater. Human communities will one day build on the land molded quietly beneath the weight of miles of ice. Through these hidden geographies, the deep history of ice remains woven into the surface of Earth long after the glaciers have passed. When the world slips into its long winters, the oceans respond with a quiet transformation of their own. Although the surface may seem unchanged at first glance, the great waters of Earth take on new shapes and rhythms as the ice spreads across the continents. Sea levels fall, coastlines stretch into the open air, and the vast basins of the planet reveal lands that have been hidden for ages. Beneath the waves, life adapts to cooler currents and shifting habitats. The oceans become partners in the frozen cycle, holding memories of the past and shaping the future of the planet. During an ice age, the growth of continental ice sheets locks enormous amounts of water away as snow and compressed ice. This slow but steady capture of water causes the oceans to shrink. Global sea levels drop by hundreds of feet. The change is not sudden, it unfolds across centuries, then millennia, as ice climbs higher and higher upon the land. Yet the effects are profound. Entire shorelines move outward, bays transform into coastal plains, coral reefs become stranded above the waterline, bleached by air and sun after millennia beneath the waves. These lowered seas reveal sweeping land bridges that connect continents once separated by water. In the north, the most famous of these is the Great Land Bridge that once joined Asia and North America, stretching from the coast of Siberia to the far edge of Alaska. Wide grasslands covered much of this vast region. Herds of mammoths, bison, and other grazing animals roamed across it in long migrations, followed by human groups who carried with them their tools, stories, and hopes. The ocean floor, dry and cold under the glacial sky, became a highway of life. Farther south, other land bridges appeared. Australia connected with New Guinea. Southeast Asia merged into a single sprawling landmass. Islands that today sit far apart became stepping stones across continents. Birds, mammals, and early humans used these routes to spread into new territories. The oceans, by retreating, opened paths that shaped the history of life on Earth. The coastlines themselves changed in character. Shelves that today lie beneath shallow water became exposed ground. In some places, these new coastlines were steep and windswept. In others, they formed gentle slopes that stretched for miles. The oceans pulled back from cliffs that had been carved by ancient waves. Beaches moved far from their old boundaries, leaving behind terraces, fossils, and deposits of sand that marked their former positions. Beneath the surface, the oceans cooled. Colder air from the expanding ice sheets touched the waters, gradually lowering temperatures across the globe. These cooler waters could hold more dissolved carbon dioxide, pulling it from the atmosphere and storing it deep within their currents. This subtle exchange played a role in sustaining the glacial climate. The oceans became vast carbon reservoirs, quietly holding the gases that once warmed the air above. As the waters cooled, Marine life adapted in intricate ways. Many species moved toward lower latitudes, where temperatures remained more stable. In places where cold currents dominated, plankton communities shifted. Some species thrived in the cooler, nutrient rich waters, others declined or migrated along the changing boundaries of temperature. These shifts in plankton rippled upward through the food chain, influencing fish, seabirds, mammals, and everything that depended on the productivity of the seas. In the deep ocean, circulation patterns changed. The cold surface waters grew denser and sank more readily, strengthening certain parts of the ocean conveyor belts that transported heat and nutrients around the globe. Elsewhere, meltwater from advancing glaciers entered the oceans, forming layers of fresh cold water that disrupted normal mixing. These changes influence the flow of deep currents that, over long timescales, help regulate the climate of the planet. Along continental margins, habitats stretched into new shapes. Kelp forests shifted their ranges as the oceans cooled. Coral reefs, sensitive to temperature and sea level, faced cycles of decline and renewal. When sea levels fell, many reefs were left high and dry, unable to survive exposure to air. But in deeper waters, new reefs began to grow where sunlight still reached through the cool, clear water. These patterns of loss and rebirth shaped the ecosystems that would reemerge when the Ice Age ended. The tides also behaved differently. With lower sea levels and altered coastlines, the patterns of tides across the world shifted. Estuaries shrank, and river mouths extended far from their original openings. Wetlands that once lay along gentle coasts became inland plains. Salt marshes dried or moved to new positions farther out. Migratory fish, such as salmon, encountered river systems that stretched longer distances and offered new challenges. Everything along the meeting place of land and sea adapted to the shifting rhythms. The open ocean itself remained a place of immense life and movement, even in these colder times. Marine mammals followed the changing edges of sea ice. Seals and whales traveled through waters transformed by new currents and temperatures. Some species expanded their ranges into cooler waters that had become more hospitable. Others retreated into protected basins. The oceans were never still, even when ice gripped the continents. Their vastness allowed life to reorganize, adapt, and move across regions shaped by deep time. When the ice sheets eventually began to melt and retreat, the oceans rose again. Land bridges submerged, coastlines moved inland, marine habitats shifted once more. Nutrients stored in glacial dust and sediments were carried into the seas, feeding new bursts of life. The ancient shorelines vanished beneath the waves, becoming memories held in stone, fossil, and the quiet structure of the sea floor. The oceans breathed out carbon as they warmed, releasing it back into the air. Through these changes, they played an essential role in lifting Earth out of its glacial cold and into a new interglacial world. In this long story, the oceans reveal themselves as patient partners in the rhythm of ice and warmth. They rise and fall with the breath of the planet, shaping continents, guiding life, and storing the deep memories of the Earth's ancient winters. When the world settles into its long winter, the atmosphere becomes a different companion than the one we know today. It grows thinner in its moisture, heavier with drifting particles, and shaped by winds that follow altered paths around the globe. Above the frozen landscapes and the shrunken seas, the sky carries the imprint of the Ice Age as clearly as any glacier on the ground. To understand those ancient winters, we can lift our gaze upward and listen to the air itself. During deep freezes, the atmosphere holds far less water vapor than it does during warm periods. Cold air simply cannot carry much moisture. Even in places far from the ice sheets, the humidity sinks until the air feels light and crisp, almost empty, Clouds become thinner and less common, rainfall declines, snow still falls, but often in slow, dry flurries rather than heavy storms. The world becomes quieter under these conditions, filled with long stretches of pale, cloudless sky. This dryness affects every part of the land. Plants must survive with less water. Soils lose their moisture quickly, turning dusty and fragile. Rivers shrink in some regions, and in others they carve deeper channels as meltwater and glacial runoff concentrate into narrow paths. The atmosphere, unable to hold much water, allows evaporation to slow. Lakes linger longer in the cold, but slowly lose their warmth. Every cycle of wind and cloud reflects the simple fact that cold air is a poor keeper of moisture. As the continents dry, the winds pick up dust from vast plains. These particles drift upward into the atmosphere and travel across entire hemispheres. Dust becomes one of the most characteristic features of the Ice Age sky. It thickens the air in subtle ways, softening the sunlight that filters through it. The dust comes from exposed shelves where sea levels have fallen, from deserts that expand in the cold, and from the bare soils left behind by retreating glaciers. Each grain of dust carries the memory of distant landscapes, carried far by winds that know no borders. Some of this dust eventually settles into the oceans, where it fertilizes plankton and influences the planet's carbon cycle. But much of it remains suspended for long stretches, turning sunrises and sunsets into muted displays of color shaded by the particles drifting across the sky. The atmosphere becomes a storyteller, holding layers of history in its very haze. The winds themselves shift as the planet's temperatures fall. Jet streams, the powerful rivers of air that circle the globe, move into new positions. They slip farther south in the northern hemisphere and farther north in the southern hemisphere. These changes reflect the contrast between warm tropics and frigid poles. In an ice age, the difference in temperature between low and high latitudes becomes sharper. The atmosphere responds by tightening and redirecting its high altitude winds. These altered jet streams reshape weather patterns across continents. Storm tracks shift along with them, following paths that feel unfamiliar to our modern eyes. Regions that today receive steady rainfall may become cold and dry. Other areas, especially those near the edges of the ice sheets, may experience intense but infrequent snowstorms during certain parts of the year. The movement of these winds controls the delivery of moisture, the direction of storms, and the patterns that govern climate. Closer to the surface, winds sweep across open plains that stretch farther than they do in warm ages. With sea levels lower, the distance between inland regions and the ocean increases. Marine air travels longer paths before reaching land. This creates wide belts of continental climate, where temperatures swing sharply between seasons. Summers remain short and cool. Winters stretch long and deep. These surface winds gather dust, sculpt dunes, and carry the cold far into regions once moderated by the sea. Over the polar regions, the atmosphere becomes a dome of frigid, dense air. This polar dome acts as a barrier, guiding the movement of weather systems around it rather than through it. The boundary between the cold polar air and the warmer air farther south forms a zone of turbulence. Storms gather along this line, feeding on the temperature differences and following it across continents. The sky, shaped by this uneven distribution of heat, becomes a map of the Ice Age climate. The reduced humidity also alters the chemistry of the atmosphere. With fewer water molecules, the air becomes cleaner in some ways and dustier in others. Carbon dioxide levels fall as colder oceans absorb more gas. This contributes to the cooling, gently reinforcing the conditions that allow the ice to remain. Even the clarity of the sky changes. In many regions, the reduced moisture creates crisp views across long distances. Mountains appear sharper, horizons seem farther away. The atmosphere takes on a clarity that feels almost weightless. Yet despite the dryness, the cold, and the dust, life continues under this sky. Plants adapt to the thinner water supply. Animals move through landscapes shaped by wind and cold. Human ancestors study the clouds, the wind, and the signs of approaching storms, learning the rhythms of the Ice Age atmosphere. They become experts not only in the land beneath their feet, but also in the sky above their heads. In time, as the ice sheets retreat and the oceans rise again, the atmosphere softens. Moisture returns, dust settles, jet streams climb back toward familiar paths. Warm air spreads across the continents, filling the sky with new forms of life and new patterns of weather. But the memory of those cold skies laden with dust and shaped by powerful winds remains in the layers of ice, in the sediments of ancient lakes, and in the quiet knowledge held by the planet itself. The atmosphere in an ice age is a world of light dryness, drifting particles, and winds that bend around the ice. It is both harsh and delicate, shaped by the slow unfolding of Earth's long winter, and holding within it the whispers of landscapes far below. As we move deeper into the story of Earth's long winters, we eventually reach a moment where the planet's ancient rhythm meets a new and unusual force. For millions of years, the timing of the ice ages followed patterns shaped by sunlight, orbit, oceans, and the slow breathing of the planet's own systems. But now, for the first time, one species has begun to influence that rhythm in ways that no life form has ever done before. Humans, through the gases released into the air, have become part of the delicate balance that decides when the next great winter will arrive. To understand this new chapter, we can begin by imagining the atmosphere as a thin blanket wrapped around the world. During the past glacial cycles, that blanket grew slightly thicker or thinner depending on how the oceans moved carbon and how the planet warmed or cooled. These changes happened slowly, guided by natural forces working over tens of thousands of years. Today, the blanket is growing thicker much faster, warmed by greenhouse gases released from burning ancient fuels, clearing forests, and reshaping the land. Carbon dioxide is one of the most important gases in this blanket. It absorbs heat and prevents some of it from escaping into space. During ice ages, the levels of this gas were low, allowing heat to slip away more easily into the night of space. When the planet moved into warm interglacials, carbon dioxide rose gently, adding a bit more warmth and supporting ecosystems that spread across continents. These changes were gradual, unfolding over long stretches of time. Human activity has altered that pace. In only a few centuries, carbon dioxide levels have reached heights last seen long before the great ice sheets of the recent cycles ever existed. This increase has added warmth to the atmosphere, shifting Earth's climate in measurable ways. The warming is rapid compared to the slow bends of natural cycles. Because of this, scientists have begun to study how this new pulse of carbon might influence the next ice age. Their findings are surprising. Many studies suggest that the rise in carbon dioxide caused by human activity could delay the arrival of the next glaciation. Earth was slowly approaching the point in its orbital pattern where northern summers would weaken again, a condition that helped snow linger year after year and eventually build into ice. This gentle decline in summer sunlight is one of the early signals that, in the past, allowed glaciers to begin their long advance. But the increase in atmospheric carbon has added warmth to the planet's surface. Even small amounts of extra heat can influence whether snow survives through a summer. At the threshold where the climate teeters between cooling and warming, this added warmth may tip the balance. Some researchers propose that the carbon released over the last few centuries is enough to postpone the next major ice age by tens of thousands of years. In their view, the Earth was drifting toward colder conditions, but greenhouse gases have nudged it back toward stability or even further warming. This does not mean the planet is free from long-term cycles. The orbit continues to shift, the tilt continues to change, the wobble continues to turn like a slow celestial dance. These forces will remain part of Earth's story for as long as the planet orbits the Sun. But the climate responds not only to orbital rhythms, it also reacts to the composition of the atmosphere itself. Greenhouse gases can reinforce warmth or ease the passage into cold. They act as a quiet but powerful influence, one that humans have amplified in ways that natural cycles never expected. The question then becomes one of balance. How much carbon can the atmosphere hold before the natural triggers of an ice age lose their strength? At what point does human influence overshadow the subtle tilt and wobble that once guided the planet into its great winters? Scientists continue to explore these questions using ice cores, ocean records, and complex climate models. They compare ancient patterns with modern changes, searching for clues that reveal how close Earth lies to its glacial threshold. This threshold is delicate. During the past ice ages, the planet cooled enough for snow to remain year after year in the far north. Once that happened, ice grew and reflected more sunlight, cooling the world further. But if summers stay just warm enough to melt that snow, the cycle does not start. The trigger never pulls. Even slight shifts in greenhouse gases can have lasting effects on whether the snow survives or disappears. Human activities have altered this starting point. By adding heat to the system, we may have pushed the threshold upward. Instead of slipping slowly toward conditions that allow ice to grow, the planet now moves along a warmer track. The balance between warmth and cold becomes more fragile, not because the cycles have vanished, but because our influence reaches into the same system that once shaped mountains of ice. Still, there is a quiet complexity to this story. The carbon added to the atmosphere today will not remain forever. Over thousands of years, the ocean will absorb some of it. Rocks will slowly remove more through chemical reactions. Forests, soils, and future ecosystems will play their parts as well. The planet has ways of balancing itself over long time spans, yet the timing of these natural processes may not match the pacing of our influence. In this mixture of ancient forces and modern change, Earth enters a new moment in its history. The next ice age, once guided by steady rhythms and patient cycles, now encounters a world warmed by human decisions. Whether that warmth delays the cold for millennia or alters it in subtler ways is still unfolding. What remains clear is that for the first time, humanity has stepped into a role once held only by natural systems, shaping the future of the planet's long winters through the air that surrounds us all. To understand where we stand in Earth's long rhythm of ice and warmth, we must return to the present moment and see it through the quiet lens of deep time. The world around us, with its familiar climates and seas, rests within a rare interval of comfort. This warm chapter is known as the Holocene, a period that began a little more than 11,000 years ago when the great ice sheets finally loosened their grip on the continents. Since then, Earth has enjoyed a gentle stability that allowed forests to spread, rivers to settle into predictable paths, and human communities to rise and grow. The Holocene is not the first warm pause in the long sequence of ice ages. There have been many before it, yet it is one of the most stable. Temperatures have shifted, but not with the wild swings seen during glacial times. Instead, the Holocene has unfolded like a quiet breath held between the long winters, a space where ecosystems could rebuild and where humans found the conditions needed to cultivate plants, domesticate animals, and begin shaping landscapes in new ways. To picture the Holocene, imagine the Earth shortly after the last glacial maximum. Ice still clung to the northern continents, but the world was warming, meltwater rushed along fresh rivers. Grasslands spread into valleys once buried under frozen weight. Lakes formed in basins carved by ice. The oceans rose steadily, reshaping coastlines and filling places that had once been dry plains. As the ice retreated, it left behind a world ready to be claimed by forests, wetlands, and fields of green. Across this warm period, Earth's temperature has followed a gentle arc. After the large ice sheets melted, the planet warmed quickly at first. By about 9,000 years ago, temperatures reached early Holocene highs in many regions. Forests stretched far north, even into places that today feel too cold for such growth. The air held more moisture, rainfall patterns shifted, creating fertile lands in regions that are now deserts. Human communities flourished in these conditions, living among lakes, rivers, and coastal plains that offered food, water, and shelter. In the middle of the Holocene, temperatures cooled slightly. Over thousands of years, the planet drifted toward a quieter and steadier climate. By the time recorded history began, Earth's temperature was lower than it had been during the early Holocene warmth, but still well above the deep glacial cold. The climate remained stable enough for agriculture to develop along the floodplains of great rivers, for settlements to grow into cities, and for cultures to spread across continents. Over the last few centuries, temperatures began to rise again. This recent warming is rapid compared to the slow curves seen in natural cycles. It is linked to human activity, but even before the modern era, the Holocene's warm pulse was already nearing the point where in past cycles the planet began its long slide toward cold. This makes our current moment unusual. The conditions that once signaled the approach of a new ice age now overlap with conditions shaped by the greenhouse gases added to the atmosphere since the beginning of the Industrial Age. To understand where Earth sits in its natural rhythm, scientists compare modern orbital conditions to those present at the start of earlier ice ages. They examine how sunlight strikes the northern continents during summer, especially at high latitudes, where snow can survive the warm season. In past cycles, when this northern summer sunlight weakened, snow remained longer each year. Over thousands of years, these lingering snow patches grew into layers of ice, then into glaciers, then into the vast ice sheets that defined the deep freezes. Today, the amount of summer sunlight reaching the northern lands is gradually weakening once more. By orbital geometry alone, Earth is on a path similar to the ones that preceded earlier glaciations. The tilt of the planet is slowly decreasing. The wobble that changes the direction the poles face is shifting in ways that gently cool northern summers. The shape of Earth's orbit is also approaching one of its long cycles that favors cooler conditions. In other words, by orbital timing alone, the seeds of the next ice age would normally be forming right now, yet the climate is not responding as it once did. The warmth of the Holocene remains. Snow that falls in the far north melts each summer. Ice sheets have not begun to grow. Instead of drifting toward cold, the planet has risen into a warmth that does not fit the pattern of the past. This divergence reveals one of the most delicate truths of the climate system. The orbital rhythms set the stage, but the atmosphere decides how the story unfolds. And the atmosphere we live in now is different from that of past cycles. It holds more carbon, it traps more heat, it pushes Earth away from the threshold that allows snow to linger year after year. Scientists study this threshold closely. They compare the present day with periods in the past when conditions were similar. They look at how much carbon the atmosphere held during those times and what the temperatures were. The conclusion they reach again and again is that Earth today does not resemble a world preparing for ice. Instead, it resembles an interglacial extended beyond its expected lifespan, its warmth sustained by a combination of natural cycles and the influence of human activity. This does not erase the ancient rhythm. It only alters the next step. The cycles still turn, but the climate responds differently because the atmosphere carries more warmth than the orbital conditions alone would provide. In deep time, the planet will continue its dance around the sun. The tilt will rise and fall, the wobble will turn, the orbit will slowly stretch and then round again. But for now, within the gentle cradle of the Holocene, Earth lingers in a warmth that has allowed life and human civilization to flourish. This is where we stand in the long cycle, in a warm interval that has lasted longer than many before it, shaped by both the ancient pulses of the planet and the recent changes brought by human hands. The next chapter will unfold slowly, as all chapters in Earth's story do, guided by forces that operate over thousands of years and by choices being made in the present day. To understand where Earth is headed, scientists look not only at the warmth of the present, but also at the faint beginnings of the long cycles that once guided the planet into ice. The world around us feels stable compared to the deep glacial past, yet the ancient rhythm continues beneath the surface. It moves slowly, almost imperceptibly, shaped by the tilt of the planet and the orbit that carries Earth around the sun. If the next great winter were ever to begin, its earliest signs would not arrive in sudden storms or dramatic shifts. They would reveal themselves in quiet changes that unfold year by year, century by century. Scientists study these changes like soft echoes of a distant future. One of the first signals lies in the far north, where summer sunlight determines whether snow melts or survives. In past cycles, the seeds of ice ages began with small amounts of snow that refused to disappear through the warm months. As the planet's orbit slowly reduced the strength of northern summers, snow lingered longer, turning to ice and building layer by layer. Today, scientists watch the Arctic with careful attention because it acts as a sensitive indicator of these changes. Arctic summers have grown warmer over the last century. Sea ice that once covered the ocean through the warm months now melts more completely each year. The remaining patches of ice are thinner than they used to be. Snow on land does not last as long. These trends run opposite to the early stages of past ice ages, when snow thickened and spread. If the planet were drifting naturally toward colder times, scientists would expect to see longer lasting summer snow in the far north. Instead, each summer brings more melt, earlier thawing, and greater exposure of dark ocean water that absorbs heat and deepens the warmth. This pattern suggests that the Arctic, for now, lies far from the threshold that would allow ice to grow. Yet scientists do not look at snow alone. They also study the Great Conveyor Belt of the North Atlantic, a current that carries warm surface water northward and returns cold deep water southward. This current helps shape the climate of the northern hemisphere. It softens winters in Europe, influences rainfall patterns, and distributes heat across the oceans. During glacial cycles, changes in this circulation played important roles. At times, bursts of meltwater from northern ice sheets weakened the current, leading to abrupt cooling across the Atlantic region. In other periods, strengthened circulation carried more heat northward and slowed the advance of ice. Today, scientists observe signs that portions of this circulation are weakening. Fresh water from melting Arctic ice and Greenland's glaciers is pouring into the North Atlantic. This fresh water is lighter than salt water and can disrupt the sinking motion that drives the deep part of the circulation. Instruments placed in the ocean measure currents that are shifting subtly, not collapsing, but showing patterns of change. If the circulation were ever to weaken significantly, it could cool parts of the northern hemisphere, even as the rest of the planet warmed. Cooling in the north might help snow linger longer each summer, which in theory could support the early steps of glacial growth. These changes are slow, quiet, and complex, but they form part of the tapestry of signals that scientists watch with patience. Another important clue lies in the air itself, in the concentration of carbon dioxide that shapes the warming or cooling of the planet. During past ice ages, carbon dioxide levels were low, and during warm interglacials, they rose gently. These shifts moved in harmony with the growth and retreat of ice, never changing abruptly. Today, however, carbon dioxide has climbed far above the levels seen in both glacial and interglacial periods of the past million years. This rise has added warmth to the climate system, altering the balance that once allowed snow to survive and ice to grow. To understand how carbon dioxide affects the future of ice, scientists compare modern levels to historical thresholds. In past cycles, ice sheets expanded under atmospheric conditions much cooler and much lower in carbon than those that exist today. Even during periods when orbital conditions favored cooling, the planet required low greenhouse gas levels to allow the ice to take hold. At times when carbon dioxide rose above a certain threshold, ice sheets stopped advancing and sometimes retreated. These comparisons reveal that present day carbon levels sit well above the range associated with natural glacial beginnings. This means that even if Earth's orbital pattern were to reach a point that once supported snow growth, the atmosphere of today would resist that shift. Summertime heat would melt snow before it could accumulate. The warmth trapped by greenhouse gases would overpower the gentle cooling from orbital changes. Scientists often describe this threshold as a balancing point. On one side lies the cooling influence of orbital cycles, on the other lies the warming influence of carbon. The present moment leans strongly toward warmth. Snow that might have survived under ancient conditions melts quickly in the modern climate. But the study of these signals does not end with any single factor. Scientists weave them together, creating a picture of Earth's position in the long glacial cycle. They watch the Arctic summer melt because it reveals how close the planet lies to the snow survival threshold. They measure the North Atlantic circulation because it influences the distribution of heat and the potential for cooling in key regions. And they track carbon dioxide levels because this gas determines how much warmth the atmosphere carries and how easily ice might grow. These signals do not predict the distant future with certainty. Instead, they offer quiet clues, glimpses into the conditions that once shaped the rise of glaciers and the fall of sea levels. For now, they show a planet far from the threshold that allows ice to return. Summers in the far north melt more snow than they preserve. The oceans hold patterns of warmth that spread across continents. The air carries more carbon than it has in many thousands of years. Yet the ancient cycles continue beneath these changes. The Earth still tilts, wobbles, and drifts through its long orbit. The world remains part of the same celestial rhythm that has guided it through countless glacial ages. Scientists watch these signals with gentle patience, knowing that each contains part of the story of how the next chapter might unfold. To understand the future of Earth's great winters, we must step far beyond the present moment and allow our thoughts to drift across stretches of time so long that human history becomes only a thin thread. The rhythm of the ice ages has lasted for more than 1 million years, a slow pulse guided by the planet's orbit, tilt, and the gentle balance of sunlight across the hemispheres. But no rhythm lasts forever. Even cycles that feel ancient and unbreakable can change, fade, or vanish entirely as the Earth continues its long journey through space and time. If we look at the near future in the language of geology, the planet still sits within the same pattern that has created the 100,000-year cycle. The orbit will continue to shift between more circular and more elongated paths. The tilt will rise and fall. The wobble will keep turning like a slow lantern swinging in the dark. These motions are written into Earth's motion around the sun, and they unfold with steady patience. By this measure alone, the 100,000-year rhythm would continue. Glaciers would return someday. Ice sheets would grow. Seas would fall. Then the cycle would turn again toward warmth. But the planet is not shaped only by its orbit. It is shaped by continents that drift, mountains that rise and crumble, oceans that open and close, and volcanic systems that breathe heat and gas through the crust. These forces work on timescales that stretch into the millions of years, yet they carry the power to reshape the conditions that allow ice ages to form. Even the familiar pattern of the last million years began only after older cycles gave way to new ones. Before that shift, Earth followed a slower rhythm of 41,000 years, when the tilt of the planet dominated the climate. It was only during the mid-Pleistocene transition that the deeper and more dramatic ice ages began. This reminds us that the cycle is not fixed. It is an outcome of many moving pieces, all interacting in their own steady ways. One of the most important long-term forces is the arrangement of the continents. Ice sheets grow more easily on land than on open water. The northern hemisphere, with its wide stretches of continent at high latitudes, is particularly prone to glaciation. The southern hemisphere, dominated by ocean, does not produce the same large ice sheets except in Antarctica. As long as the continents stay where they are, Earth remains in an ice-prone configuration. But continents drift over millions of years. They inch across the planet, carried by the slow currents of the mantle beneath them. One day, tens or hundreds of millions of years from now, this arrangement will change enough that the poles may lie in different places, or the oceans may take on new shapes. With those changes, the climate rhythm may shift again, and the familiar pattern of ice ages may fade. Another geological force lies beneath our feet. Volcanic activity, especially over long periods, can alter the balance of greenhouse gases in the atmosphere. If volcanic eruptions become more frequent over geological timescales, they may release enough carbon to warm the planet. Warmth could weaken the conditions needed for ice growth. On the other hand, if volcanic activity quiets or if weathering of rocks accelerates, carbon dioxide could decline. Lower carbon levels could make the planet more sensitive to orbital cooling, deepening the ice age cycles. These changes would not happen suddenly. They would unfold across ages, woven slowly into the fabric of the climate. The deep future also depends on how the planet's orbit will evolve. Over tens of thousands of years, the shapes and timing of the cycles will continue to shift. The eccentricity cycle that drives the 100,000-year rhythm varies in strength. Sometimes it exerts a strong influence. At other times it becomes faint, barely nudging the planet at all. In the distant future, Earth may enter a period when the eccentricity cycle weakens, and the climate responds more gently to the orbital changes. During such times, the planet might follow a different pattern, perhaps closer to the older 41,000-year rhythm. If we look even farther ahead, beyond the scales of ice sheets and mountains, we eventually reach a future shaped by the sun itself. In hundreds of millions of years, the sun will continue to brighten as it ages. The increase is slow, so slow that it cannot be felt within any human time frame. But over immense stretches of time, this steady brightening will add heat to the planet. Eventually, the warmth will grow strong enough to overwhelm the cooling that allows ice ages to form. Long before the sun reaches its final stages, Earth may become too warm to sustain the vast cycles of glaciation that have shaped so much of its recent history. The familiar dance of ice and melt, cold and warm, will quiet, replaced by a world where ice sheets no longer grow to continental scale. Yet that future lies far beyond the horizon of human existence. When we speak of tens of thousands of years, or even hundreds of thousands, we are already reaching beyond the lifetime of civilizations. When we move toward tens of millions, we enter a world where forests, oceans, and mountains will look different from anything we know. The ice cycles may continue for many glacial periods to come, or they may shift into a new pattern, shaped by geology, carbon, and the long breath of the planet. But no matter how the rhythm changes, the Earth will respond as it always has, reshaping itself with the patience of deep time. In this vast future, the ice cycles remain only one chapter in a far longer story. They have shaped the world we know today, carved valleys, guided oceans, and framed the rise of human life. Whether they continue for many cycles more or slowly fade into a different pattern, their memory will remain written in stone, soil, and the quiet layers of the planet's deep history. If we look at the world around us with quiet attention, we can still see the fingerprints of the great winters that once covered so much of the earth. The ice ages ended long ago, yet their legacy remains in the shapes of mountains, in the paths of rivers, in the softness of soil beneath our feet, and even in the places where human communities chose to settle and grow. The ice did not simply melt and disappear. It carved, pushed, sculpted, and rearranged the land in ways that continue to guide life today. To imagine this legacy, it helps to picture the immense ice sheets that once stretched across the northern continents. They were not gentle bodies of snow. They were moving giants, their bases grinding against stone, their weight pressing valleys deeper, their slow flow smoothing hills and sharpening ridges. As the ice advanced and retreated, it shaped the ground like a massive chisel, carving forms that would outlast the cold by thousands of years. Many of the mountains in cooler parts of the world carry these marks. Wide U-shaped valleys cut through ranges that once held rivers but were transformed by the grinding push of ice. Their walls rise steep and smooth, swept clean by glaciers that sculpted stone in broad strokes. Cirques, those bowl-shaped basins high in mountain ranges, are remnants of ancient pockets of ice that clung to cliffs long after the larger sheets had retreated. When the sun filled those cirques and the last ice melted, some became lakes or cradles of alpine meadows. Even in flatter regions, the ice left behind patterns of gentle hills and long ridges. These features formed from debris the glaciers carried within them. As the ice melted, it released these materials, scattering stones, gravel, and fine sediments across the land. Today, these deposits create rolling landscapes that differ from the sharp features shaped by rivers alone. In some places, long winding ridges known as eskers stretch across fields, marking the paths where meltwater once flowed beneath glaciers in dark tunnels. The rivers that flow through many nations today also owe their courses to the ancient ice. When glaciers carved valleys, they made deep paths for meltwater to follow. When the ice sheets withdrew, the rivers settled into these ready-made channels. Some rivers grew strong and wide, carrying water from melting snow in mountains shaped by the Ice Age. Others formed in basins created by the weight of ancient glaciers, pressing the land downward. Over time, these river systems provided fresh water to plants, animals, and early human groups who followed their curves across the continent. Lakes are among the most striking gifts left behind by the ice. When glaciers retreated, they left depressions that filled with meltwater and rainfall. Some of the world's largest lakes, including those in North America, formed in these carved basins. Their waters reflect skies that once held only drifting snow and cold wind. Across northern Europe and parts of Asia, thousands of smaller lakes dot the landscape, each one a quiet reminder of the ice that shaped it. These lakes support rich ecosystems today. They provide water for communities, habitats for fish and birds, and beauty for anyone who pauses to watch their surfaces shift beneath wind and sunlight. Beneath our feet, the soil in many fertile regions is another gift from the ice. As glaciers ground rock into fine particles, they left behind layers of mineral-rich sediment. When the ice melted, winds carried some of this dust across great distances, spreading it over vast plains. These deposits, known as loess, created some of the most productive agricultural soils on Earth. Wheat fields, cornfields, and orchards thrive in lands once covered by glacial dust. Entire agricultural systems depend on these deep, soft soils that hold nutrients and water with gentle abundance. Even the coastlines were shaped by the rise and fall of the oceans during the ice ages. When the ice sheets grew, the seas fell, exposing wide continental shelves that stretched far from today's shores. When the ice melted, the seas rose again, flooding river valleys and creating bays, estuaries, and deltas. Many harbors that support modern cities sit in these drowned valleys, their shapes sculpted first by rivers and later by rising seas. Because of these changes, human civilizations grew in landscapes shaped directly or indirectly by ancient ice. Early peoples followed rivers that traced glacial valleys. They settled near lakes that filled freshly carved basins. They farmed fertile soils made from glacial dust. Later, cities rose in river deltas, molded by the shifting seas of post-glacial times. Some of the earliest trade routes followed paths left behind by melting ice. Even today, roads and railways often trace the gentle grades formed by old moraines and outwash plains. The ice ages also influenced the climate zones that humans inhabit. As glaciers retreated, forests spread northward. Grasslands expanded in their wake. These shifting ecosystems opened new pathways for migration and settlement. The habitats that emerged after the Great Melt nurtured species that would become essential to human life. The plants and animals we rely on today, from grains to grazing mammals, thrived in environments shaped by the cold that came before. In this way, the legacy of the ice ages is not ancient or distant. It is present in every valley carved by glaciers, in every river shaped by meltwater, in every fertile field enriched by glacial dust, and in every settlement built upon land molded by cold hands long ago. The modern world is built upon these gifts, even if we no longer see the ice that created them. Across the quiet landscapes of today, the memory of deep winter remains, etched into the surface of the earth and woven into the story of life. As we arrive at the quiet end of this long and drifting journey, it is comforting to pause for a moment and feel the world around us as it truly is. We are living in a rare kind of warmth, a gentle intermission in a planet-wide story that stretches far beyond anything humans have ever witnessed directly. The ground beneath our homes, the coastlines we walk beside, the rivers that wind patiently toward the sea, all carry memories of a colder earth that once held a very different shape. For many chapters now, we have slowly moved through the story of ice and sunlight, of slow orbits and deep oceans, of dust carried by wind and carbon carried by water, of glaciers that grew like great white continents and then melted until their last fragments became the lakes, soils, and valleys that shape our lives today. Through each step, the rhythm continued to return, always circling back to that familiar pattern of long winters and short warm breaths. And here we are, resting inside one of those breaths. The warmth of the present day, the landscapes we recognize, the climates we rely on, all exist because the planet is between glacial pulses. This is not a permanent condition. It is a quiet space in a much longer cycle, one that stretches across tens of thousands of years. The warmth that surrounds us is not fragile, but it is temporary. It is a page in a story still being written. When we remember this, Earth feels older, steadier, almost patient. The planet does not hurry. It drifts through its cycles with the slow grace of something that has been turning through space for more than 4 billion years. It tilts, wobbles, shifts its orbit slightly, and responds with long stretches of cold or gentle spans of warmth. These movements are so small that no single lifetime can feel them, yet their combined influence has shaped nearly every landscape we know. It can be humbling to imagine that even our most dramatic histories, the rise of cities, the growth of societies, the paths of our ancestors across plains and mountains, all unfolded during a fortunate pause in the cold. This warm chapter has allowed forests to spread wide, rivers to find stable courses, and ecosystems to flourish in ways they could not during the deep freezes. It gave our species time, space, and resources to grow into the world we now call home. Thinking of this can bring a soft sense of wonder. For all our noise and movement, we are living within a brief island of calm, carried gently through time by the planet beneath us. The next great winter may be distant, perhaps postponed by human influence, perhaps arriving far later than it would on its own, but the rhythm will continue eventually. Earth will follow its ancient patterns, as it always has, and the landscapes will shift once more under the slow hand of ice. Yet none of this is meant to bring worry. If anything, it reminds us of how quietly connected we are to the planet's deepest rhythms. We stand on land, shaped by cold that melted before the earliest stories were ever told. We drink water carried by rivers that settled into channels carved by glaciers we never saw. Even the air, thin and soft around our heads, carries the signature of warmth that came after long ages of frost. We live surrounded by gifts from times far beyond memory. As this story settles and becomes still, I want to thank you for drifting through it with me. These late night explorations are made special by your presence, your curiosity, and the peaceful space we create together. If you would like to join me again for more slow journeys through science, I would love for you to subscribe. Your support helps keep this quiet corner alive, and every new listener becomes part of this gentle community that rests and learns together. If you are already subscribed, thank you for returning to these calm nights and wandering through Earth's long history alongside me. Your comments, your thoughts, and your quiet company mean more than you might imagine. Now let your shoulders loosen. Let your breath move softly in and out, steady as a tide returning to shore. The story of ice and warmth can continue its slow drift in your mind, fading like the last glow of evening light. You are safe here, resting inside the warmth of a planet that has carried life through cycles far older than memory. And with that, I wish you a peaceful night and gentle dreams until we explore again.